Yes, I can hear you.
So, sorry, Susilo, Professor Susilo, I was sorry. I am very sorry because you see, I was having problem to joining through the link.
Oh, okay, all right. That's
Okay, sir, should I start? Yeah, because you see, there was some problem. I am unable to join. So, I am sorry, very sorry for that. Okay, so let us start, sir. Busy, sir.
okay. So can I
Hello,
start? Can I start now?
sir. Busy, sir, is there? Hello, hello.
Yes,
Prem
sir.
Kumar, VC sir is there. So let us
Yes,
start.
sir.
So welcome and good afternoon to everybody. I am Dr. Debashish Giri, Associate Professor in the Department of Abul Kalam Azad University of Technology. And the program is jointly organized with the University of Abul Kalam Azad University of Technology and the Islamic University of Science and Technology. I am the program coordinator of the event. And in our inaugural ceremony, we are having our Honorable Vice Chancellor, Professor Soikat Mitra, and we are having four speakers, Professor Willie Surino, University of Wollongong, Australia, Professor Rakesh Verma, University of Boston, USA, Dr. Susmita Ruj, Tata 61, Australia, Dr. Yang Lee, the University of Electrocommunications, Tokyo, Japan. So now since we are already delayed, now I request to our Honorable Vice Chancellor to say few words to the participants. Hello, sir.
Yes, Gary.
Uh,
So,
yes,
thank
sir.
you.
So you just say few words.
Yes. Actually, we're late in initiating and starting this program today because of some technical snags. However, we could make it. But now the thing is that today in this series of webinars on the cybersecurity, cryptography, this is probably the sixth one. So sixth, so sixth,
10th one.
tenth,
10th.
tenth one.
Yes, sir.
So this is this remarkable thing from the university and from this cybersecurity unit Department of Information Technology of this university that numbers of these webinars have been organized in recent past in this particular domain, and this and it is very important also in this current context. And I told in previous webinars also the same thing. The importance of this cybersecurity is becoming more and more, this prominent in current context because the digital things, that is digital platforms and digital technology, digital techniques that are becoming part and parcel of our life. Therefore, our security of our data, security of our entire digital system, that is of prime importance now. And as everything, our personal details, financial things, our this all sorts of activity, even manufacturing systems, everything now relying more and more on these digital techniques, digital processes, and which is a part of Industry 4.02. And the next revolution in industry will be Industry 5.0. There also these digital tools, techniques, and all these things that will be very this in a predominating role, particularly in making the systems more automated, applications of robotics, remote controlling process, and healthcare systems everywhere. These digital techniques are now, this only formidable option because of this pandemic scenario. In near future also, this trend will continue even if the situation become normal, because this improves the efficiency and this improves the accessibility to digital technology. But at the same time, the hazard is this security. Therefore, uh, there are many studies conducted by different chamber of commerces and professional organization, consultancy firms, and from the report, it is quite evident that in India we need this lakhs and lakhs of cyber security professionals, either in the form of this for cyber auditing, for this for ethical hacking, or restoration on the entire things, so to like cyber forensics, and in many areas, this opportunities and I know the scopes are increasing, then applications of integration of cybersecurity, the cybersecurity is emerging as you know this as a full-fledged subject as such. Earlier, it was a part of this one of the component of our computational science, computer science and engineering or information technology. But as more and more components are being added to it, so it is evolving as a separate discipline of academics. And many university institutes introduced programs, specific programs on cybersecurity, either for undergraduate, postgraduates, science programs, technology programs, certification programs, diploma programs, PG diploma programs in the various branches of cybersecurity. And we have also, following this trend. In the recent past, we have introduced many programs in cybersecurity to cater the need of the future demand in the cybersecurity professionals in the country. And I'm very happy that now we need to strengthen our activity further, because this is the situation where a common people, starting from a common people, start to up to these executives of multinational organizations, bureaucrats, administrators, police personnel, everyone, they should be aware of this, these different these aspects of these cyber threats and cyber problems. And for them also, to make them more aware, we need to have more types of different types of these programs. And in doing that, we need to develop large number of professionals who will make them aware. Only these persons with adequate knowledge in these particular disciplines and in allied areas, they will be able to transmit their knowledge for the betterment of the society. So this is for this endeavor, I would like to congratulate Dr. Giri. Now this one of the tasks is now left to publish a compendium of all these 10, and maybe in near future more webinars will be organized in this line, and kindly try to publish one compendium compiling all the lectures delivered by different resource persons with these transcripts, written transcripts of all the lectures, so that it will be this very useful for our learning community, and it will be a learning document as well. And another interesting thing for this digital platform is we created a discussion forum. Now there is an opportunity of creating one cybersecurity community, a collaborative community. Here, I'd like to request you again, kindly, engage yourselves in developing network, because you see, we need to, enlighten ourselves and empower ourselves with more knowledge, more ideas, more innovative ideas, more creative ideas. And I have seen that in today's context, even students who are from high schools, they have also these brilliant ideas. So what are the innovative ideas? What are the different sorts of ideas? How to use all these ideas? How to take a this leading role in making all these innovative things integrated to make it formidable in the context of the entire world. Small countries, they are dominating in the world in the fields of technology, and we have enough manpower, enough demographic dividend, enough potential, human resources, intellectual potentials. We should take the lead now, right now, and we should be able to go to a position where the world will come to us for taking our help and guidance in the domain of cybersecurity. That is our one of the dream and mission, and for that we have to take this massive effort. And our university, Dr. Giri and others, our faculty members, we have our HOD IT, Professor Sundata Chakraborty, our other members of our director of school, they are working hard to make this activity of the department very useful for the society, for the community. And we have our knowledge partner, IUST. We have other partners as well. We have strategic relations with CDAC, Government of West Bengal IT Department, with TCG groups, and we are trying to collaborate with many other professional groups to make this entire effort more formidable, more structured, and more useful for the society. So with this, I wish you all the best. My sincerest thanks to the resource persons again, because they are kindly consenting to deliver their lectures, sharing their knowledge. Delivering lectures at webinar platform is not so easy. They have to take lots of preparation for that. So they have to take lots of pain for that. So my sincerest thanks to all of them for taking this pain and burden, responding our call to remain present at this digital platform for sharing their news, for sharing views and ideas. And this is the beauty of digital platform. because we are in a position to invite people from different corners of the world, and many participants from different parts of this country, different parts of the state, different parts of the world, they can also join as learner. So this digital platform, this immense potential of digital platform, this boundaryless situation, the timeless situation at any point of time, even at this weekend, Saturday, at at this time, there's at this part of country there's festive season, but still I can see lots of people have assembled, and this timeless and numberless, boundaryless features of digital platforms has made all these endeavors more visible and more this attractive. Now we believe that out of all these exercises in near future we will have this enough numbers of knowledge repository as well as enough numbers of experienced, enthusiastic and energetic cybersecurity professionals for safeguarding the interest of common people, for safeguarding the interest of organizations, community and the country. Thank you all.
Thank you, sir. Thank you very much for your valuable speech to the participants. So we are having the fourth speaker today, Professor Willie Susilo and Professor Rakesh Verma. Rakesh Verma is from USA, and now in USA, I think it will be around 2:30 a.m. So he will be joining later. And next, Dr. Susmita Ruj and Dr. Yang Lee. Now, today's first speaker is Professor Willie Susilo. Dr. Willie Susilo is a senior professor in the School of Computing and Information Technology, Faculty of Engineering and Information Science at the University of Wollongong, Australia. He is the director of Institute of Cybersecurity and Cryptology, School of Computing and Information Technology, University of Wollongong, and he is the head of the School of Computing and Information Technology at the university from 2015 to now, till now. Prior to this role, he was awarded the prestigious Australian Research Council Future Fellowship in 2009. In 2016, he was awarded the Researchers of the Year at University of Wollongong due to his research excellence and contributions. He is the editor-in-chief of the LSBR Computer Standards and Interface and the MDPI's Information Journal. He is currently as associate editor of IEEE Conjunction of Dependable and Secure Computing. He has also served as the program committee of several international events. Now I request to Professor Susilo to start your presentations. You are most.
Okay, all right. So can you hear me there? Yeah.
Yeah. I'm sorry for that. Okay.
Okay. That's okay. So maybe just to save the bandwidth, I will not turn my camera if it is okay. So let me share my screen. Okay, so can you see my screen?
Yes, it is coming, sir.
Okay, all right. Okay. So let me start the presentation. Right. So my name is Willie Susilo. I'm from the Institute of Cybersecurity and Cryptology at the University of Wollongong, Australia. So we are actually in New South Wales. It's located about 1 hour from Sydney. So today, actually, I will present some of this is one of my recent work that is entitled PKMET. Then is public key encryption with multi-ciphertext equality tests in cloud computing. So what this is about, so I will explain this term later, right, when we talk about this. Right, so this presentation is based on the recent work that I just mentioned. Basically, this work just been accepted in IEEE transaction on cloud computing. So if you are interested on the detail, actually that there is a link there, then actually you can find, or you can just search on the title, then you will find this paper, right? If you want to extend this work somehow, just like this is a new notion that actually we invented. This is joint work with my co-authors, Dr. Fujun Guo Dr. Chao Zhen, and Dr. Ge Wu. All right, so this is actually the structure of the talk. So I'll discuss about why we want to do this, and I'll describe the so-called PKE MET and how to construct this. And later on, I'll show you briefly about the PKE FMET. If we have time, I'll show you about the construction briefly, but in detail, you can check at the paper. Okay, so basically, before we discuss about the new notion on PKE MET, we need to understand first about the notion that's called PKEET. This is public key encryption with equality test. This notion was proposed by one of my colleagues, is Dr. Bo Min Yang, and his co-authors in CTRSA 2010. So the main idea is this primitive, this cryptographic primitive, will allow us to compare whether two ciphertexts they actually contain the same plain text or not, but without being able to decrypt the ciphertext. So essentially, the idea is we want to have the power to compare whether two ciphertexts are originated from the same plain text or not. But of course, the tricky part here is we do not want the tester to be able to decrypt the ciphertext. Because if we can decrypt the ciphertext, then basically you can see the plain text, right? So that's why it is actually formulated like what is shown in this picture, that user A actually has an encrypted database, user B also has an encrypted database, and then A and B actually they own the database with the encrypted file, and then A and B actually want to authorize a tester in the middle here, so that the tester can actually test whether this the ciphertext that they own actually is coming from the same plain text or not. But the tricky part is without being able to decrypt the ciphertext. So the idea is basically user A will generate an authorization token that's given to the tester, and similarly user B will give the authorization token given to the tester. So the tester, by having two authorization tokens, then the tester will be able to check whether the ciphertexts are actually coming from the same plain text or not, without being able to do decryption. So actually, that's the idea of the primitive that was introduced in CTRSA 2010 conference. Why this primitive actually becomes popular? Because in fact, this primitive can be used in cloud computing. So essentially, the idea here is in the previous picture, when I show a tester, the tester in fact can be the cloud. So basically, the cloud server will act as the tester, and then the users will authorize their token to the cloud server. And then eventually the receivers, by sending the token to the cloud server, the receiver actually want to test whether those ciphertexts are the same or not. So the idea is to give you a simple application is, for example, suppose that there are two people take a picture, take a photo together, and then A upload the file, encrypt it, B upload the file also encrypted, but A encrypt with his key, B encrypt with his own key. So obviously the ciphertext looks different because they are encrypted with different key. But now the receiver actually want to test first if those photos are actually identical. Then actually the receiver want to save their bandwidth, so that the receiver actually will ask the cloud to test whether those two photos are the same or not. If they are the same, then the receiver will just download one copy of the photo rather than downloading two copies of the photo, right? So that's the idea when we use in the scenario of cloud computing. So it's similar to the scenario that we discuss usually in the sense of data deduplication when we talk about cloud computing. So that's PKET, and this PKET in fact has gained a lot of attention from the researchers. There are many variants of the original PKET, which is public key based. There is identity based version, there is attribute based version. Actually, last year We created the lattice-based version, which is post-quantum secure, that we got past paper award in the ACISP conference on this construction. So there are many construction that's available in the literature that extended this PKET. So what is this primitive that I want to explain to you now? Basically, this new primitive is actually based on the extension of PKET. So the extension is like this. Now, if the cloud server want to verify the equivalence of n ciphertext, so basically, in the previous scenario, I've mentioned that two people, they take photo together, and then A and B, they upload their photo. The photo is encrypted with with A's key, and the second one is encrypted with B's key. So obviously, the result is different. But now, what about, suppose that we take a photo together in a conference, like this meeting, we have so many people, and then in this case, now a lot of people, now we want to upload this photo together to send to the cloud. So what we want is the same thing. The cloud will need to test whether all of the ciphertexts are actually originated from the same plain text. So actually, it's a very simple and natural extension of PKET. So how can actually we solve this problem? Basically, this problem naturally can be solved with PKET. So for example, what we do is we check first, the cloud will test, is the ciphertext CT1 and CT2, they are actually coming from the same plain text or not? If the answer is yes, then they will continue, the cloud will continue. Is ciphertext CT2 and CT3 is the same or not? The answer is yes. Then now, is CT3 and CT4 the same or not? Coming from the same plain text or not? And so on and so forth, until we compare CTN-1 with CTN. Okay, so this one actually will work, this procedure. However, there is one drawback. In fact, there are two drawbacks in this case. The first drawback is, suppose that CT3 is the different one, right? So we have CT1, CT2 up to CTN, they are all the same. CT3 is the different one. So when the cloud actually compare, is CT1 the same as CT2? The answer is yes. Now, is CT2 the same as CT3? The answer is no. Now, is CT3 the same as CT4? The answer is no. Is CT4 the same as CT5? The answer is yes. So eventually the cloud will know that the one that is different is actually CT3. So here is basically what I listed here. In fact, if I use normal PKET, this will actually lead to heavy computation overhead. Why? Because the cloud actually has to do PKET for n-1 times. So because for every single pair, the cloud has to do this comparison. So that means n-1 times. And additionally, the most undesirable feature is the cloud, in fact, will be able to find out which ciphertext which actually contain a different plain text. That's actually what we don't want to happen, because the purpose of the cloud is to test whether those ciphertexts all are coming from the same plain text or not. So the cloud should be able to just say yes or no without any additional information, right? That's why the PKET is unfortunately cannot be used to solve this problem. So this is why we introduced a new primitive which we call PKEMET. So basically in PKEMET is a public key encryption with multi-ciphertext equality test. So essentially the idea is precisely what we have just mentioned earlier. So the idea is we want to reduce the computation overhead, and we also want to eliminate unnecessary privacy disclosure. Then that's why we intend to design a system to perform the equality test only once, just only once on all the n ciphertexts. So we don't want to have n-1 operations, but we want only one operation on all of those n ciphertexts, and the operation will need to return the final result. The final result will just say yes or no. And the structure, actually the framework is the same as PKET. Basically, as you can see in this picture, sender 1 will send all the CT1, sender 2, CT2, and so on. And then each of the receiver will authorize, give the authorization token. And then just the cloud will just have to give one answer, is 1 or 0. And that's it, right? No additional information that will be leaked to the cloud. Actually, that's the only purpose. And interestingly, this simple and straightforward question that is based on the PKET primitive, in fact, the solution is not trivial. So actually, it's not really easy to create like this. That I will show you next. So I'll start with the definition of PKET. Basically, we have the following algorithms. First one is the setup. Setup algorithm will output the system parameter as usual. That's the normal like PKET. We have a key generation that will produce public and secret key pair, PK and SK. And then the encryption is the main difference with PKET. In the encryption, we give the parameter public key and the message, and we add one parameter which I call designated number S. So essentially it means that it will output a ciphertext CT on message M under the designated number S. What does it mean by designated number S? Such that a quality test on CT can only be performed if and only if we have S-1 other ciphertext or designated numbers which are S. So to give you an example, suppose that if someone encrypt and put S is equal to 3, that means if we want to execute the equality test on this particular ciphertext, then we will need two other ciphertexts which will have the same designated number, which is equal to 3. This is similar like the notion of secret sharing, right? The notion of secret sharing. So basically, if we have such ciphertexts, and then based on those 3 ciphertexts, now we will be able to conduct the equality test. If we do not have enough ciphertexts, then equality test cannot be done. So the next algorithm is algorithm on decryption. So given the ciphertext CT and the secret key SK, it will output either the plain text M or the decryption failure. So the next algorithm is the authorization algorithm. Given the secret key SK, it will actually output a token DK as what is shown in the picture. So the same as PKET, which is the authorized key to the cloud server, such that it can perform the equality test on the ciphertext of user who owns SK. So this particular one is the same as PKET. So in PKET, we also have this procedure in which the owner of the secret key will need to output a token DK. And now we go to the algorithm that's important, which is the test algorithm. So this test algorithm will require a set of ciphertext that's I denoted as CT1 to CTT. So here is suppose that CTI designate as I, where I become between 1 to T. Then basically we require that all of those T will have the same designated number S. So in this case, then if we can find those CTs, those ciphertexts in which the designated numbers are actually the same, then we can conduct the test, and the test will only output yes or no, 1 or 0, that will imply whether those ciphertext CT1 up to CTT, they are actually equal or not, right? But it doesn't actually output anything else, given all the appropriate tokens. So next, I want to show the correctness of the PKET. So that the first one is about decryption correctness. So obviously the decryption must be correct. So what we require is that for any security parameter lambda, any message M in M, and any number designated number S, we will have that if the setup algorithm is executed correctly, if the keygen algorithm is produced correctly, and we encrypt with the correct S, then the decryption with the secret key SK will always produce M with probability 1. Right, so additionally, for the same security parameter lambda and any message M as well as T, where I is between 1 to T, then if we do the setup correctly, keygen correctly, and then we encrypt with designated number T, so that means we will require T ciphertext here with the same designated number, which is T, and then all the authorization from the SKI when 1 to T is given as TKI. That means we have TK1 up to TKT. This test, the probability that this test is equal to 1 will be overwhelming. And then additionally, if one of these messages is actually not the same, if one of the messages is not the same, then basically this test will output 0 with the overwhelming probability. So if all the messages are the same, then this will be 1. If one of them is not the same, then this will be 0. All right, so now I want to discuss about the adversaries, the adversaries for PKMET. So in the traditional PKET system, if you are not familiar with PKET, basically there are two types of adversaries, which is type 1 and type 2 adversaries. So basically in type 1 adversary, it will adaptively make any token queries on any user. So we can query any token queries on any user, such that it can test the underlying messages equality on any ciphertext. So the goal of type 1 adversary is to find the underlying message given a ciphertext. So if we are given ciphertext, then we need to find out what's the underlying message, like the decryption, basically, if for the decryption, that the attack against the decryption algorithm. So type 2 adversary is actually doesn't allow the adversary to make token queries on the target user, but the goal is actually to distinguish the underlying message of a given ciphertext between two known messages. So essentially, the adversary will need to distinguish whether two messages that's given from two ciphertext, it will look different to the adversary or not. So these two types are actually existing in PKET system. And in the PKMET system, we will actually adopt these two adversary as well, because that's the basic requirement for PKET. But specifically for PKMET, we introduced the type 3 adversary for PKMET. Basically, this adversary will try to perform the equality test on T ciphertext. On T ciphertext, basically we have CT1 up to CTT, where all the designated number of S, in fact, the designated number of S is bigger than T. If the designated number S is bigger than T, technically this adversary will not be able to conduct the equality test, right? Because we will require that S must be less than or equal to T in order for the test to be able to be executed. So formally, actually, the security model is defined like this. This is exactly like what I just explained earlier. So essentially, the adversary will be restricted to make a secret key query on PK star. That's the public key of the target. Then we need to define the adversary of winning the game is as we want to find whether the original M star. Right? So basically, whether the adversary can decrypt the message or not. That's type 1. In type 2 adversary, the adversary is not allowed to make the secret key and token query, but we want the adversary to be able to distinguish the messages that's been given. So as we can see in this game formally, when we encrypt, so that there will be the adversary will output two messages, M0 and M1, and then we pick one of these to encrypt to become CT star, and then the adversary can still do still use the previous all the previous public key and this oracle, and the adversary need to output this bit. Except the adversary cannot ask the oracle for the PK star. right? So that's actually indistinguishability game. So this third one is the new one that we define, which we call number game, to capture the type 3 adversary. So essentially it means that basically the adversary cannot make any secret queries on all of these public keys. And then what we want is if the designated number is in fact bigger than the number of the ciphertext that's available, the adversary will not be able to conduct the test. So basically, the adversary need to be able to win this game with this probability if the number of S is actually, we have the S is bigger than T here. All right, so now I want to briefly talk about how we actually construct this PKMET construction. The construction actually is very interesting because in fact it looks very easy, but in fact it's not easy to create this kind of construction. So the construction actually looks like this. It's actually our first scheme. The setup is as usual. We have G, prime order of P. We have generator of G, and we define the 3 hash functions. And then the keygen, in this keygen, keygen will output public key and secret key. So here we will have 2 random numbers, X and Y, which is actually the 2 secret keys. Why do we have 2 secret keys? Because we use X as the encryption key, Y as a testing key. So basically, one key is used for the decryption. Another key will be used for testing. And then encryption actually is the most tricky one. So in order to allow later on to do the test all together with so many ciphertexts, what we do is like this. So if we give the target S, right? So that's the basic number S. We need to actually iteratively compute like in this picture. So basically we iteratively compute this one. F0 is the hash of M concatenate with S. F1 will be the hash of M concatenate with S concatenate with F0. F2 will be the hash of M concatenate with S concatenate with F0 and concatenate with F1, and so on until Fs minus 1 is hash of M concatenate with S concatenate with F0, F1, F2 up to Fs minus 2. What are the purpose of this F, this constant F, sorry, this parameters F? So in fact, by having these F's now, we can set a new polynomial like this. So we let Fx is equal to F0 plus F1x plus F2x squared and so on. So this polynomial will be used to do the encryption. So the encryption actually will work like this. This is a trick where we can achieve a constant size. So here basically we set C1 is G to the R1 is a random number, and C2 is hash of X R1. So if you remember X is G to the X. So X to the power of R1 XOR with M R1. So later on what we want is if I get C1 and C2, if I know the secret key X, basically I will be able to retrieve this M. How can I retrieve M? I will need to do C2 XOR with C1 to power of X. And I take the hash of C1, right? C2 will be XOR with the hash of C1 to power of X. Then it will cancel this one. Then I will get M R1. Why we want to put R1 here? This R1 later on can be used to check to achieve the security in the proof later on, that this R1 later on we need to check that this G to the R1 will be equal to C1. All right, so that will be used for decryption. So for the C3, C4, C5, this is designed to do the testing. So C3 is G to the R2. C4 is very similar to this one, the structure. C4 is hash of y to the R2. So again, similar to this, but we use y. But this is the tricky part, is we XOR it with A concatenate with FA, where A is a random number. So basically, we find this polynomial from here, and then now we pick a number A, random number. Then we need to compute FA, and we get this. And after we get C3 and C4, so now we set C5 to be the hash of all of these parameters, C1, C2, C3, C4, y to the R2, and F0 up to Fs minus 1. So the whole ciphertext, as you can see, is a constant size, is S, C1, C2, C3, C4, C5. Right? Even though this one looks very long, but the ciphertext, in fact, at the end will be a constant size. So here, in fact, the CT can be performed in equality test with other S-1 ciphertext, in which all with the designated number S. Right? So when we want to do this, C3, C4, C5, we can only do the equality test when we have found S-1 ciphertext with the designated number is equal to S. I will show you how later. So the decryption is what I said earlier. So basically, decryption is very easy. C2 XOR with hash of C1X. Once we do the decryption, then actually we can recompute this one. F0, F1, F2 up to Fs minus 1, obviously. And then we can check all of these equations, whether they are all correct or not. So decryption actually is very easy. So in this scheme, decryption is not the main thing that we are talking about, because what we are talking about is mainly about the test. So the next one is the authorization algorithm. When we give the secret key SK, we need to output the authorization token. So the token here is very easy. The token is actually Y. We give out Y, but we don't give X. Right? X is used for decryption. So this part is actually the tricky part when we want to do the test. When we want to do the test, we need to have CT1 up to CTT, where all of each CTI, they are all of the form of this SI, C1, C2, C3, C4, C5. Right? And then we need to have the corresponding token, which is C1, C2, C3 up to CT. And then this will update the equation if any of these S is not the same. So basically, if any of the S is not the same, then we cannot conduct the test. Right? We need to have the designated number to be the same. So how can actually we preserve this? So basically, we can see that from C4 and C3, because C4 and C3, if I go back to here, from C4 to C3, you can see that from this structure, in fact, I can get a hash of C3 to the power of Y. That will cancel this part. Then that will leave me with A concatenate with FA. Okay, so that's exactly what I'm doing here. So A concatenate with FA. So that means that if I have the CT, I have CT ciphertext, I will have T out of this pair. Right? I will have T out of the pair. Meanwhile, each of these Fi will be equal to FI will be equal to Fi0, Fi11 AI, 12 AI squared up to Fi t minus 1 AI t minus 1. Right? So basically, because we have T out of them, each of them will correspond to this polynomial. If I have T out of them, I will have these T equations. These T equations come with T unknown. Right? So there are here, there are all of these A1 up to AT minus 1, they are all unknown. Right? So essentially, when we do this, when we will find a unique solution, because in fact, this is the equation. We have T equation, And then all of this, so the number actually, this is like the matrix is actually a Vandermonde matrix. So that's basically what I wrote here. So essentially, we will be able to find a unique solution. Once we find the unique solution, we can use that unique solution to check whether C5 is correct or not. If C5 is correct, that means then it means that M1, M2 is they are all equal, and we need to return 1. Otherwise, we return 0. Okay, so that's actually the construction. So this is the correctness. So the correctness of the decryption actually is shown like this. When we implicitly setting like this, that's basically we have T equations. With each of every equation, we have T unknown. So basically, we have T squared here. We have T equations. So basically, this is our Vandermonde matrix, right? So once we have this, definitely, if I calculate this, the determinant is not 0. Because the determinant is not 0, then I will be able to find the solution with this probability. And then, if all the M's are the same, then we will be able to satisfy all of the C5 correctly. Then we have the test will be equal to 1. If any of this M is not the same, then it means that later on, when we calculate C5, there will be some issues because there are 2 equations that cannot hold simultaneously. So that means that one of these must be wrong. If one of these must be wrong, then the test is equal to 0. Right? So that's, I think, is quite straightforward from the basic linear algebra. So the security proof, basically, we prove from type 1 is based on CDS assumption. So actually, is a very standard assumption in here. The type 2 adversary is based on CDS assumption, and number security is based on information theoretical sense security. So it's just like in the secret sharing scheme. So the main drawback of the PKMET is basically due to the designated number S. So here, actually, I'll briefly talk about this. We still have some time, so I can talk about this just briefly. We can continue with the PKE with flexible multi-ciphertext equality test. So basically, PKMET only allow equality tests to be performed on S ciphertext, all that will designate S. Right, so to enable the system to be more flexible, we want to extend PKE-MET to a flexible version that we call public key encryption with flexible multi-ciphertext equality test. So what it means is the setting is the same. The senders actually send all the ciphertext, and then the receiver actually send the token. But now we require that the sender doesn't need to use the same designated number. The only requirement is we just want to make sure that this S that we have here must be less than the number of T. If S is bigger than T, then definitely we cannot do it, as what we have seen before. But if S is less than or equal to T, so in the previous PKMET, S has to be equal to T. But here is as long as S is less than or equal to T, we will be able to do the test, right? That's actually the purpose of PKE-FMET. So in PKE-FMET, we can perform equality tests on T ciphertext, even their designated number SI are different, as long as the maximum number of designated number S is less than or equal to the ciphertext number T. So essentially, the number of ciphertext is very important. So if we do not have enough ciphertext, then obviously later on, when we come to the Vandermonde matrix, as what I've shown you earlier, we will not be able to find a unique solution. Therefore, we cannot do the test, right? That's why we need to make sure that the designated number S is less than T. So the main difference with FMET compared to MET is in the following algorithm. In the setup algorithm, it is not just outputting system parameter, but the parameter should also include a number n, which will denote the maximal number of ciphertexts that can be performed equality test on. So basically, this is the maximum number of ciphertexts that we can perform the equality test on. And then in the test algorithm, there is a slightly change. So we still have T ciphertexts and T tokens, but we want the designated number CTI to be SI, so can be different for every single ciphertext. But if S is bigger than T, definitely we cannot outdo anything. So the output is fail. Otherwise, so if S is less than or equal to T, it will output 1 or 0. That will imply whether the message of these ciphertexts are equal or not. So how can actually we achieve this FMET? So before we do into that, so the decryption and the testing correctness actually can be seen like this. The decryption actually is the same as before, but correctness is slightly different. So here we have a parameter now that we require S should be less than or equal to T, and S must be less than or equal to 10 in the parameter. Then we can do the test. If it is 1, it means that all these messages are equal to 1, are the same. Then the probability will be overwhelming. And subsequently, in the same setting, this test will be equal to 0 if and only if one or more of these messages actually is not the same. So basically, M1, M2, M3 up to MT, they are not equal. This probability is overwhelming. So in this particular setting, we use type 1, type 2, type 3 adversaries. But additionally, we add a type 4 adversaries that is defined like this. Because in type 4 adversaries, essentially this is to model an adversary who want to conduct equality test on T ciphertext, CT up to CTT, but T actually is less than S. So basically S is bigger than T, right? So obviously the adversary should not be able to conduct this test, but we need to model it in this type of adversary, type 4. This one, again, it doesn't exist in the PKE-MET. Of course, it doesn't exist in PKE-ET. So this is actually the new number game. So the adversary is not allowed to make the secret key queries on all of these public keys as before, but now we require the setup here that S is actually bigger than T, still less than N. Then we want that this the advantages of this is the probability of P prime equal to B minus half. Okay, so it's not better than the random guess. So the construction, basically, how can actually we can get construction? Construction, we can achieve a trivial construction. So trivial construction can be achieved from the PKMET. So the idea is like this: we add the maximum number n, such that the equality test can be performed. And then we see that C1, C2 are used for decryption. C3 is just used for to hide the random number. In C4, C5, what we can do is in the PKE-MET, we need to compute all the other pairs for n minus s pairs. So basically, we will need to add the pairs for s plus 1, s plus 2, up to n with the same computation as the original C4, C5. And then in the test algorithm, we need to verify the correctness of all of the C5. So this one actually will work. This one actually will work. Well, we can achieve this F8MET. However, the main problem is it will sacrifice the ciphertext size and computation efficiency. What do I mean by that? Is you can imagine that suppose that I have a designated number which is very small. I have a designated number very small. For example, I said S equal to 2. Then if n is equal to 10, I will need to add 8 because 10 minus 2 is 8. I need to add 8 dummy pairs of this. 8 dummy pairs of this. So that means no matter what the size of S is, then I need to make it to be equal to N. So basically to make the size to be the same as N, which is the maximum. This is in fact the same technique that is used in the Labrie paper in Asia Crypt when they talk about how to do the broadcast encryption, right? So if you are familiar with broadcast encryption, actually, in fact, Cecile de Labrie proposed a method like this to make sure that we can achieve a broadcast encryption with different parameters. So there's actually, so this is what I said, and this trivial construction will sacrifice the ciphertext and computation efficiency. So it's like even your S is very small, you will need to add a lot of dummies parameters. That means there will exist a negative linear relationship between the ciphertext size and the designated number, such that the size of the ciphertext will designate a small number will be very large. So obviously, this is something we don't like. So therefore, we actually invent a new construction which actually will achieve constant size. So we don't need to add those additional ciphertext. So the trick here is actually like this. The setup is the same, but we add a one hash function here. So the keygen is the same. The encryption, so this is the first step of the encryption of PKMET. But after we do this, now we create several levels. So this is the levels we will create from F0S up to F0N. Basically, this is the one that we get all the coefficient. We hash this to produce this one. We hash this again to produce this one, and so on up to here. So essentially, we will have a set of this function now. Instead of just one set of parameters, we will have a set of parameters. So essentially, it means that for one number, for one ciphertext, we will have a set of these functions. So here, that means that instead of having one, which is FA, remember in the previous construction, we have A and FA. Now we will have FSA, FSA plus 1 up to FNA. So the construction actually is the same as before, except the exception is here. In the previous construction, we XOR with A, FA. But now we will XOR with A, FA, FSA from layer S, concatenate with FA from layer FS1, so basically the next layer, and concatenate with FS plus 2, and so on up to Fn. So this is because it's a number only, just one number. You XOR this, and then C5 will contains the hash of all of this, but now this is all of this F are here. So because this is like, it looks long in this case, however, the result here is still constant because the result is still the same length as PKE MET, which is 6 components. And for decryption remain the same, right? But now for the decryption, we will achieve all of this one, and then we can check all of this to return this, right? So that's actually obvious. Authorization is still the same. We just output Y. The test actually is more tricky because in the test, we use C3 and C4. When I use C3 and C4, I will get this one, C4 XOR with hash of CT to the power of this token. Then I will get this, all of this. And when I get this, basically I can extract all of this component. When this component are extracted, basically you have a set of equations. You have set of equation like this. And again, we need to compute, based on this, we need to find the solution, unique solution. Once we find the unique solution, then now we check whether C5 is still the same as all of the solution. If yes, that implies that the message is all the same. Otherwise, it returns 0, which means the message is not the same. But the nice thing about this method is basically it does not leak anything. So to the adversary will not be able to know which message is actually different, right? So actually that's the nice thing about these two construction. And then in this construction, we deliberately do not use pairings, or we do not use post-quantum cryptography. So we use the basic setting first, because if we can use in the basic discrete lot setting, that's actually the best, right? So obviously we can solve this problem in a little bit more elegant if we use pairings, but of course pairings will cost more compared to the normal discrete lot. Yeah, so the correctness actually is very obvious. So when we get the test, so we get this, we get all of this component, we can extract all of these parameters. Then after that, we form this matrix, and we have S equation for S unknown. That means you find the solution uniquely, then you can do the test, and the probability will be overwhelming. If one of these M is not the same, that means later on we will have the two equations that cannot hold simultaneously, the same condition as what we have seen earlier. That means the test actually will fail. So that's it from me. And again, if anyone is interested to know the detail, especially I don't have time to talk about the proof. So this is actually the paper. This PKEMET, feel free to extend this, or if you want to have any discussion with me, you can send me an email. I think we can easily construct a pairing-based version. We can also make it more efficient based on that, right? With that, I close this talk. Thank you.
So thank you, Professor Will. From the participants, any questions is there? From the participants, you are having any question, you can directly ask or put into the chat box.
If any questions is there from participant side, please post it in the chat box, or you can directly ask the question by unmuting your mic. And if you don't have any question, we can move to the next session. Sir, we can move for the next session.
So thank you, Professor Wiley Sosilo, for your nice presentation, and it is very informative, and it will be helpful to our participants surely. And you see, student participants, if you are having any questions, you can send to his mail. I will hope that he will give the answer. So thank you, Professor Susilo, for your nice presentation, and busy schedule, you are able to present your talk.
Yeah, you are most welcome. Thanks.
Okay, thank you. Okay. So now we are going for the next speaker. Next speaker is Dr. Yang Li. Yang Li received his PhD degree in engineering from the University of Electrocommunications, Japan in 2012. From 2013 to 15, he worked as a research assistant professor at the University of Electrocommunications, Japan. From 2015 to 18, he worked as an associate professor at the Nanjing University of Aeronautics and Electronics, China. Currently, he is an associate professor in the Department of Informatics and at the University of Electrocommunications, Japan. His main research interests include security evaluation and implementation for cryptographic hardware and IoT device. So now I request to Dr. Lee, you start your presentation. Yeah, Lee.
Sorry. Can you see my screen?
Yes, it is visible.
Okay. So can I start my presentation now?
You can start, Dr. Lee.
Okay.
Yes, sir.
Okay. Hello everyone. My name is Yang Li. I come from the University of Electrocommunications, Japan. I'm a Chinese, but I'm now working in Japan. And it's an honor for me to be invited to give you a talk here. So different from the first talk, my talk is giving a general idea of what I'm doing and the research our team's going. So the title of my talk is Physical Attacks and Their Countermeasures, and Unfinished Story. So you can see that my talk is basically focused on the physical attacks and on cryptographic devices. Okay, first I'm giving a general introduction of the background. So as mentioned, as the purpose of this webinar, so cryptography are actually used everywhere in our daily life. For example, here we can specifically look at the smart cards we are using. For example, when we take subways, when we're using transportation systems, we're using some smart card to pay for the money. So in China, we also use some this kind of smart card to identify ourselves. For the banking system, we using all the bank cards, and for cell phones, we use a SIM card to identify the number system. So all these small smart cards are actually have some cryptographic algorithm implemented inside it. These devices are very small, and the calculation power is not very great, but still we want to run some cryptographic calculation inside it. So when we look at these devices, we can consider them as just cryptographic devices. And the important thing here is that there is some secret information stored in this card. And this secret information is very important. If this information can be extracted by an attacker, then the attacker can actually produce the exactly same card. So all the security behind these systems will be broken. So all these cryptographic devices are just, we can consider it as a simple model. They're using a secret key and giving an input and do some calculations to give the output. And as an attacker, they want to extract the secret key here. So when we're talking about the security of these devices, the problem is how can we recover the secret key? And when we're talking about this recovering of secret key, it's called cryptanalysis. And generally, cryptanalysis can be divided into two types. The first type is well known is mathematical cryptanalysis. And the talk I'm going to focus is physical cryptanalysis. The difference is that in the mathematical approach, it's considered that only we are trying to find the weakness in the algorithm itself. So it's the security is discussed in a black box model. It means that for the algorithm, only the input and output can be accessed by the attacker. So the intermediate values cannot be accessed. So actually, this setting is very difficult because all the algorithms have been well designed and also been tested by many researchers. So actually, it's quite difficult to be successful to break some practical devices. But on the other hand, for the physical cryptanalysis, the model is much relaxed for the attackers, because attackers not only be able to access the input and output of the calculation, also he can understand some information of the intermediate results during the calculation. And this kind of information is actually very useful for the attackers to extract the secret key. So actually, there are practical attackers that can practically break some real devices using the physical approach. So in this talk, I'm going to focus on the physical cryptanalysis here. So basically, there are two types of physical attacks it's called side channel attacks and fault attacks. The general difference is here. For the side channel attacks, it's a passive attacks. It means when the cryptographic device is doing some calculation, the attackers only observe this calculation. He try to gain some physical information leakage from the calculation, and they don't they don't do other things to the device. So for example, what kind of information can be extracted is like the calculation time, the power consumption, or the electromagnetic radiation of the calculation. So this is passive types of attacks, which is usually called side channel attacks, because the main channel is input and output. So otherwise, there are side channels to get the information for the attackers. So it's called side channel attacks. The other type of attack is called fault attacks. So compared to the passive attacks, fault attacks are actually active attacks. It means that the attackers don't just observe the calculation. Actually, he will try to do something to the calculation, to do some physical information interference to the calculation, to make the original calculation to become some other calculations. So it's kind of like fault injection. It just lets the normal calculation to become a faulty calculation. So by doing this way, they can extract some faulty output or other informations to help them to extract the key. So how can an attacker to do some fault injection? There are many approaches. For example, he can use some glitch in the clock signal, or using glitch in the power supply. He can use open the package of the chip and using some laser shot to inject some calculation fault. Or he can use some electromagnetic interference to introduce some irregular current into the device so that the calculation will become faulty. So, okay, so by far I have explained the background of my talk. Basically, we are talking about side channel attacks and fault attacks. And this talk, what I try to explain is that I will give a general overview of the, try to explain some basics about side channel attacks and fault attacks, and some general countermeasures against this type of attacks. Then I will try to explain some examples that when we're trying to propose some countermeasure against one type of attack, it's quite interestingly, this kind of proposal usually sometimes can lead to a new type of attack, which is quite interesting. So in this talk, I'm trying to explain 4 examples that some countermeasures that lead to a new attack. And some of these works are from our team, but some of them are not. But generally, I will just try to explain some basic ideas of them. For details, you can try to find the related papers of them. Okay. So for the first part, I will try to some more details about side channel attacks. So for side channel attacks, the basic assumption is that the attacker has some physical access to the physical implementation of a crypto system. Then he can try to obtain some information when the crypto system is working. The idea is that this kind of attack doesn't need to be like running brute force of the full key. So the calculation complexity is not very high. Also, this type of attack doesn't need to require the weakness in the original attacked target. So even algorithm, cryptographic primitive are well designed, but if it's not well implemented, then side channel attacks could be possible. So theoretical weakness is not required. As I mentioned, there are many side channels that can be used for the attack. For example, the timing information, the power consumption, the electromagnetic radiation. For some research, even the sound of the device or the heat of the device can be used to extract the key. But among all these side channel informations, most used one is the power consumption. This is the most basic and most generally used side channels. And by measuring the side channels like power consumption, what attackers can obtain is like he can understand what kind of operations, what kind of instructions are actually performed. Also, he can know some information about the intermediate values, what kind of data has been proposed, and what address has been read, something like that. Yeah, it's quite powerful. And based on the attack assumptions, there are generally two types of side channel attacks. It's non-profiling side channel attacks and profiling side channel attacks. What's the difference? The difference between them is that whether the attackers has the identical device of the targeted device. If the attacker can access an identical device, which he can freely change the key or change the plain text, what he can do is that he can study the device. He can try to understand what kind of information, what kind of power consumption will be measured based on what kind of data being proposed or being calculated, what kind of secret key being calculated. So he can try to understand the leakage profile of the target device. Then he can use this leakage profile to perform the attack against the targeted device. For the non-profiling side channel attacks, the attackers don't have the identical device of the targeted device. So what he can do is that he can just use some general leakage model based on general knowledge of the device, try to attack. What kind of, for the general leakage model, there are two types of model are very powerful and very easy to understand. The first one is a Hamming weight model. It means that generally in this model, it believes that the power consumption is going to be proportional to the numbers of bit one of processed data. If the processed data has more ones, it has more power consumption. Basically, it's a very rough model, but it's very accurate for many CPUs. So the other type of leakage model is called Hamming distance model. It's similar to Hamming weight model, but the difference is that we are trying to check out not the number of ones in processed data. Actually, we are trying to check the number of bit flips of the processed data. So we are looking at two calculation states and how many bits has been flipped between these two states. Then the more bits flips, then the power consumption will become more. Then this Hamming distance model is actually very accurate for some hardware implementations, especially for the flip-flops in the hardware implementation. More bit flips means more power consumption. Basically, using this kind of very simple models, we already can perform very powerful side channel attacks. If we can have the identical device of the target device and learn the leakage profile, then the profiling side channel attacks become more powerful, so that even more less measurements is possible to identify the secret key. So there are many variations of power analysis, and the basic idea is that how many measurements has been used. If the device, for some certain implementations, the key recovery actually is very easy to be performed. Then in this case, we can just use simple power analysis, which means that the key, the secret information, can be identified from just one or few measurements. That's enough. So this is a especially simple attack. But this is not generally working. So for the general working attack, it's called a differential power analysis. The idea is that because the attacker can access a device and to do the measurements, he can do a lot of measurements given because he have time, he want to attack to recover the key. So by doing a larger amount of measurements, then he can do some statistically processing to all these measurements and try to identify the difference caused by processing different intermediate values. So even the difference is quite small and the noise is quite large, it's fine because we can take a large amount of data and do statistically processing. So this type of attack is very powerful. So they are also very powerful profiling attacks called template attacks. And for some attacking some countermeasures, we can use multiple points of the measurement to do the attack. It's called higher order DPA attacks. In this case, for example, if we want to use some less measurements assumptions to do some attack, it's called generic DPA attack. So basically, the most powerful one is DPA. The basic classic one is differential power analysis. So here is just giving you the most simple example in the sidechain attacks. It's called, the target is, the algorithm is a modular explanation. Basically, what we want to do is that we try to calculate the a to the power of b, and the result is mode n, and it's stored in C. So for the modular part, it's not important. For the modular explanation algorithm, it has been used in many cryptographic algorithms. For example, RSA calculation, or for ECC is basically the same modular explanation algorithm. So there are many implementation methods of this algorithm, but one of them is like this. Basically, what we do is that first we set C equals to 1. Then from the most significant bit to the least significant bit of B, we just, according to the value of the B, and then we perform the following calculation. So if the value of B is 0, what we do is that we do a square calculation of C and store it in C. If the value of B is 1, we do a square calculation. Also, we do a multiplication calculation. So doing something like this. And the attacker trying to recover the secret of B here. So what we can do is that we can take the power consumption of the calculation. And for example, we take actually this is for some implementation, we take this power consumption. What we can see is that there are some patterns here. And it's not very clear, but if we look carefully, we can check here, this part, actually, they have 2 different types of power consumption here. And the main difference is actually the timing here. For example, here is take more times than this calculation. And this one takes more times than this calculation. Basically, we can depend based on the calculation time of this part, we can divide them into 2 types. The green calculation or the red calculation. Then according to this algorithm, we can basically identify that the green calculation actually is a square calculation. And the red calculation is a multiplication calculation. And if we can understand this by looking this power consumption, just one measurement, we can understand that the first bit of the B is actually 1 because it's a square followed by a multiplication. The next one is a square calculation only, so it's a 0 bit. Then square 0 bit, square 0 bit, then square followed by multiplication, then it's 1, then it's 1, it's 1. So this B bit usually, this value B usually has 1,000 bits, but it doesn't matter how long it has. The 2,000 bits, 5,000 bits, it doesn't matter. If we take the power consumption, we can read the bit one by one, and the secret value B can be recovered directly. And the problem of this implementation is that based on the secret value B, the calculation are totally different, and that's the problem. So later I will give a countermeasure to this implementation and I will say that that countermeasure is not good enough. So this is actually the example one. So later I will explain it. So side channel attacks are very powerful. So we have to consider countermeasures against them. So there are basically two types of countermeasures. The idea, two types of countermeasures. First is a hiding approach. The second one is called a masking approach. For the hiding approach, what we are trying to do is that for the information leakage, we try to hide them. We want this leakage to be undistinguishable, not able to be understand, or the leakage cannot be found. So how can we do that? For example, we can trying to do design some special circuit that always consumes this constant power without some dependency on the processed data. So by doing this, this hiding approach can be used. For example, there are dual array implementations, which I'm not going to explain details. They are trying to make the power consumption to be constant, but hiding approach has problems because even though theoretically it can making constant power consumption, but in practice it's quite difficult. Still, there are leakage. If there is leakage, we can use DPA attack, take many measurements and try to recover the key. So hiding approach is not very popular now. So the more popular one nowadays is called a masking approach. So in this case, we are trying to introduce randomness to the calculation. What we want to do is that we try to make the leakage to be random. So it's quite difficult. It's difficult to relate the measurement to the secret. So always we are using some fresh random numbers, and using these random numbers to max the intermediate values. So for every calculation, every execution, the calculation of the intermediate values are actually represented by some random value. So from the perspective of attackers, before masking, he can see exactly, he can try to see the leakage of intermediate value, which is exactly value. But now he can only see the leakage from uniformly distributed values. So it's uniformly distributed random values. He can take many measurements, but still the leakage looks random to him. So the attacker becomes more difficult, much more difficult. So basically, this is some basic ideas of countermeasures against side channel attacks. Then I'll explain some ideas of fault attacks and their basic countermeasures. So for fault attacks, what I explained before is that given a device, if we let it calculate regularly, normally it gives correct output. But if during the calculation, the attackers using some special method to interference the calculation, then we can get some faulty output. The calculation result will become not correct anymore. And the attackers can actually trying to recover the key using the correct output and the faulty output. And this key recovery is actually very efficient. So this type of attack is called a differential fault analysis. It's the most discussed fault attack. Assumption is that the attackers can know the correct output and the faulty output. Okay, most of these values can be known, and also the attackers know some information about the injected fault. So by the injected fault, information of injected fault, what kind of information can be known? For example, attackers can know the injected fault is a single byte fault, which means that for the intermediate value I here and the faulty intermediate value I prime here, the difference between them, data I is actually only 1 byte active. So only 1 byte of them is non-zero. Other values, other bytes are 0. So this kind of information assumption can be made because in circuit, when you're trying to inject fault, the fault happens in the byte unit. So single byte fault is actually can be achieved using many fault injection methods. Then the attackers can try to recover the key using the output, faulty output, and the data I, the information of data I, try to recover the key. And this key recovery is actually very powerful. For AES, actually, 2 faulty injections can identify the secret key using less than 1 minute calculation. Actually, a few seconds is enough. 1 faulty injection is also enough to recover the secret key. Why? I will try to explain why this kind of attack is so powerful. The basic idea is very simple. We know AES is a block cipher. The most widely used block cipher is called Advanced Encryption Standard. The 128-bit version of AES actually has 10 round functions. You need to repeat round function 10 times so that it's secure enough against crypto analysis. But for the differential fault analysis on AES, we are trying to use output, faulty output, and data I to recover the key. We can see that the fault can be injected anywhere so that we can doing some crypto analysis only on the 3 rounds or 2 rounds of AES here. So attackers can pick up the timing for the fault injection so that he can do some analysis using against only 3 rounds or 2 rounds of AES. Because 10 rounds of AES rounds are very secure, but 2 rounds or 3 rounds of AES rounds are not secure. So a simple crypto analysis can recover the secret key, and the calculation cost is very small. So this type of fault attack is actually very powerful. So still, since these attacks are very powerful, we need some countermeasures. So how can we do countermeasures? So here are some 2 basically approaches. The first one is fault detection. So by fault detection means that we have to do something to know that currently some fault has been injected so that the faulty output should not be given to the attackers. So we're trying to add some mechanism to detect the fault injection, to detect the faulty calculation result, and to prevent the information leakage. So how can we do the fault detection? Basically, most used ideas are just redundant calculations. For example, when we're trying to encrypt a plaintext P, we can encrypt a plaintext twice, 2 times, and then we try to compare the 2 times encryption results. If the result doesn't match, it means some fault has been injected. Then we will not output the faulty output, so to prevent the information leakage. Also, we can do encryption once and decryption once, so that to compare the decryption result with the original plaintext to check whether any fault has been injected. Also, we can use some error detection code or error correcting code mathematically to try to detect the fault. This is the basic idea. Another type of idea is called fault infection. It means that if some fault has been injected, it means some, like here it's how to say, here is a single byte fault, some meaningful fault has been injected. What we do is that we try to make the fault more random. We try to add some calculations so that the inject fault will be randomized and expanded to other parts of the output. So eventually, even we inject a single byte fault, the faulty output will become affected by randomized fault. So finally, we still get a faulty output, but for the attackers, the obtained faulty output doesn't have any information leakage because it has become a totally nonsense value, not meaningful, not information useful value, or something like that. These are two types of countermeasures against fault attack. So basically, I have finished explain some general knowledges about side channels and fault attacks, but the story is not finished yet because design countermeasures actually is quite difficult. Because when we try to add countermeasures to the calculation, the cost will increase, the performance will be reduced. So we have to design a countermeasure in a limited budget of area and power consumption and so on. So it's quite difficult. So when researchers are trying to propose a countermeasure, it's usually to focus one type of attack or leakage. So for a type of attack or leakage, we propose a countermeasure and we prove that this countermeasure is working. But other researchers are trying to find other approaches to attack the countermeasure. That's quite interesting of our this research world. So hereafter, I'm going to explain a few examples about countermeasures and the new attacks. That countermeasure leads to new attacks. So I have explained that for the modular explanation, the attack is possible. That the basic problem is here only when the secret bit of value b is 1, then they have to do some squaring calculations. When the bit is 0, there's no calculation here. So that's a problem. So what we can do is that we can do some easy fix for the problem. For example, we can, for the when the b is 1, we can do the square calculation. It's required. But when the b is not 1, it's 0, we can still perform the square calculation. But only this time, we don't store the calculation result to the register C. We just store the register calculation result to another register, some random register, doesn't use the register. And this D is never used in other calculations. We just do the calculation and store it in some place, not important. Then by doing this, the previous attack we're talking about cannot work anymore because there's no data-dependent calculations in this calculation. So no matter the value of the BI here, the square calculation will be performed. But this kind of countermeasure, simple countermeasure, actually leads to another type of attack, which is called safe error attack. What's happening here is that actually this countermeasure, what we are doing is that we are doing some dummy calculation to the algorithm. This dummy calculation doesn't affect the final result. So no matter this calculation result, it will not affect the final result. Adding this dummy operation, the purpose is just to eliminate the data dependency of the calculation time or the calculation power consumption. So then there's a new type of attack called safe error attack proposed. The basic idea is that we can do some fault injections to this calculation. For example, we can do the fault injection at the timing of the square calculation here. And by doing fault injections, we can identify whether this operation is a dummy or a normal calculation. Because when we successfully inject a fault at a normal calculation, and the final result will become faulty as well. When we successfully inject a fault at a dummy operation, because it's a dummy operation, it doesn't affect the final result, so we still get a fault-free output. So by doing fault injection here, we can identify whether it's a normal square or a dummy square. Then we can identify the secret value of B. So still, we add some countermeasure, but by fault injections, we can break this countermeasure easily. Then I will explain another countermeasures lead to new attack. It's fault detection. So the idea of fault detection is that, for example, here, we run the encryption twice, and we compare results. And if the result doesn't match, we just output the nonsense value, for example, 0. So the idea is here, by fault detection, the faulty output, the leakage in the faulty output can be prevented. But the problem is that, is there other information leakage source besides faulty output? And the answer is actually there is other fault information leakage here in this fault attack scenario. It's called fault sensitivity. Fault sensitivity means how sensitive of the current calculation against fault injections. It means for the current calculation, how difficult a fault can be injected, how much effort attackers need to pay to inject a fault. And it turns out for different calculation, when processing different data, the fault sensitivity actually are different. So here is another explanation of fault sensitivity. So here is the AES. When we give a weak injection, and it means that the fault injection is not very strong. For example, the laser is quite weak, then we get correct output. If we give it a very strong injection, we will get a faulty output. So what attackers can do, he can gradually increase intensity of the fault injection from a very weak state to a very strong state, and try to observe the output. So at the beginning, it's a correct output. But finally, we get faulty output. So attackers can always find a threshold here. So below this threshold, we get correct output. Above this threshold, we get faulty output. And this threshold is considered as fault sensitivity. And this fault sensitivity are actually data dependent, just like power consumption or other side channel leakage. So it can be used to recover the secret key. The importance here is that by fault detection, faulty output is not meaningful. Faulty output is not outputted by the device, but still, when the fault is successfully injected, for example, for this device, a fault is being successfully injected, then the device will output 0, even though 0 is not meaningful, but fault sensitivity can be measured for this device, so can be used to recover secret key. So you can see that fault detection cannot prevent fault sensitivity analysis. So here just another example for the actually device how for FSA works. So here is flip-flop, and there's a combinational logic. And normally at each clock cycle, the data will perform some calculation, and the calculation will be finished, and then another clock cycle begins. So in the photo injection, what we do is that we make this clock cycle to be the period to be short. So if we make this clock cycle to be this kind of short, still at this timing, because the calculation in this clock cycle has been finished, so the calculation result is correct. So if we make the clock cycle even shorter, then at this timing, the calculation is not finished yet. So the clock period is shorter than the critical path delay of this clock cycle. So we will get some faulty output. So attackers can do this test gradually and try to find the threshold here. This threshold is actually the photosensitivity that we are talking about. And we can see that this photosensitivity actually is connected to the critical path delay here in this cycle's calculation. And the critical path delay is actually related to the input in this clock cycle. And this input, we assume it's a secret input. So basically, we can measure photosensitivity to understand some secret inputs in the calculation. So just like other power consumptions attacks, so photosensitivity attacks can work to recover the secret. I don't have too much time, but I will try to skip some part and explain some important part for the following two examples. So the next example is laser sensor leads to a new type of side channel attack. So as I mentioned that in the photo attack, there's a method using laser-based photon injections. And this kind of photon injections is actually very powerful because the laser photon injection is very accurate in timing at the location. So attackers can choose the timing to flip exactly 1 bit. So in order to prevent this kind of photon injection attack, so the one type of idea is that we can add a sensor, some circuit, special circuit that can detect the laser irradiation. So this sensor, what this sensor do is that when it detects some laser irradiation, it will output some alarm signal. And this alarm signal will be sent to other part of the circuit. So for example, sent to the cryptographic part. The cryptographic will know that something happened and it will try to erase some secret data or prevent output some secret data so that photo attacks, laser-based photo attacks can be prevented. But in our recent work, we actually using a practical implementation of this kind of laser sensor. For this type of sensor, we can say that if the alarm signal can be observed by the attacker, can be collected or measured by the attacker using something like oscilloscopes, actually based only on this alarm signal, using this alarm signal, the secret information can be recovered. The AS key can be recovered. So actually, we are working together with proposer of the laser sensor. So they have some evaluation board here. So here we have a chip. This chip has the laser sensor inside, and it can output some alarm signal when it detects laser injection. So here's some animation. We can see here, this is a chip and this is a laser, just injecting laser here. When the laser is over the chip part, we can see that the alarm signal will become from low to high. We can see it again. So basically, it's how this alarm signal works. This is a signal just to identify when AES is calculated here. So when this green part is moving out from the chip, the alarm signal is low. When it's on the chip, it's high. It means that it's working properly. What we do first is that we actually trying to adjusting the position of the laser shot and adjust the strongness of the laser shot so that we can achieve a state that the alarm signal is not stable. It is low, sometimes low and sometimes high. It's not stable. And by looking at this signal that is not stable, actually we think that this alarm signal may be leaking some information of the AES calculation. So we measured many power traces only on this alarm signal, and we try to do some evaluations to this alarm signal. So I'm going to skip some of the details here. So basically what we did is we did some tests, and based on some tests, we can see that actually there is some information leakage here of this alarm signal. And then we did some tests using some key recovery model, like Hamming weight, Hamming distance model, and we can see that the correlation coefficient of the attack is actually very high, very low here. There are some peak here. It means that attack may be possible. Then we try to do the key recovery attack targeting the last AES round, the 10th round, and focusing 1 byte. And we took about 316,000 power traces, and we are be able to identify secret key without any problem. So it means that alarm signal, which is looks innocent, looks unrelated to the AES calculation, that can be used, but it can be used to perform some secret information, to recover the secret information. And we also do some additional experiment. What we do is that we're trying to check out what kind of signal actually leaking the secret information. So here's a calculation of AES, the first round to the 10th round. We will focus only on the last round of AES, and we divided the measured power alarm signal into 3 types. So what we do is that we divide it into 3 types: always high, always low, and unstable. It means that we put 2 thresholds here. If all the measured points are above this threshold, we consider this measured alarm signal is always high. Then if all the measured points are below this threshold, we consider it's always low. Other ones we consider it's unstable. And for the 316 measurement, we can see that 80% of them are always high, and the other 10% of 10% are always low and unstable. And what we do is that by using all these traces, we can identify the secret key. We already know that. But how about the attack that using only always high traces or always low traces and unstable traces? Whether the attack will be successful and how efficient will attack become. So we're doing some experiments. So the result is here. So by using all the data, we can see that for the 16 bytes of secret key, we can eventually recover all the secret key here. For the always high data, actually no key byte can be recovered. For the always low byte, we can only recover a few key bytes. But for the unstable bytes, unstable power traces of alarm signal, we can recover all the key bytes actually very efficiently compared to all data here. By doing this experiment, we can understand only that the unstable alarm signal actually is the most leakage source of the information here. So this is another example. Finally, I'm going to talk last one. Last one is so I have explained that some countermeasures doesn't work because we can find some new attacks to break this countermeasure. So how about we combine several countermeasures and to finish this story? And actually, at 2008 chess conference, there's a proposal called MMAES. It combines masking countermeasure and fault detection, fault infection countermeasures together so that it's supposed to be secure for both side channel attacks and fault attacks. And this is very combination of countermeasures looks very secure. And actually, this talk and this proposal, I think it should be talked in August, also in this webinar, because one of the inventors, Svetlana, give a talk here. And look at it by looking at the title, I think he also introduced this kind of combined countermeasures. So our interest is that whether this combined countermeasure is secure against both side channel attacks and fault attacks. So what we did is that it's an ongoing work. We actually implemented this countermeasure in ASIC chip, and we're trying to using this chip to evaluate the security. And by far, we just verify that our chip actually runs MMAES properly. So we do some setup the devices, and we can say that the AES is calculating the correct result is fine, and here is some power consumption we can measure for the AES calculation. So by doing this work, it's an ongoing work. We are not having some. We are not able to break this yet, but an interesting point is that we know that this masking method is that it's called threshold implementation. It's work against side channel attacks, but there's a problem that whether this threshold implementation is secure against the fault sensitivity analysis I just introduced. And for this question, actually, we find two versions of answers by two papers. So for the first paper, which is presented in 2018, it says threshold implementation is secure against the FSA. But interestingly, in this year, 2020, there's another paper that says that threshold implementation is not properly secure against the FSA. So that's quite interesting because still people are arguing whether this masking is secure against the FSA. And because due to the time limitation, I'm going to skip the ideas of these two papers. But by reading these two papers, our understanding is that the threshold implementation is not probably secure against the FSA attack. So we cannot prove that TI is secure against the FSA. But if we try to apply FSA attack to our TI implementation, it's going to be very difficult because still there are some data dependency delay, but the difference is very little, and this delay can occur with very little probability. So actually, it's quite difficult to apply FSA on TI, but still we are trying to work on it. So it's still an unfinished story. So I'm going to try to give a summary of my talk. So side channel attacks and fault attacks are very powerful. We need to propose countermeasures, but design countermeasures is quite difficult because we cannot, if we try to do a lot of things by countermeasures, then the area, the cost, the power consumption, the overhead will become not tolerable. So when we're trying to solve one problem, and it usually creates more problems. So how can we do that? It's it's a unfinished story yet. So I think the security should be achieved from a more systematical level, and by combining these countermeasures, it's actually a very promising approach. but still we need to do more research to understand, to finish this story. Okay, that's my talk. Thank you very much for your attention. So I'm happy to answer if you have any questions.
But any question is there?
So yeah, I got a question if you don't mind.
Okay.
Okay, sure. You can directly ask the question.
Sure. So for the alarm signal where you were able to show that the unstable traces are leaking the most of the information,
yeah,
I would guess that just the physical design of the alarm signal was not really properly done, in the sense that there was still some side effect or correlation between the AES computation and the alarm signal, right? I mean, this is my guess.
Yeah. Your question is actually very good. How can I say? Yeah, actually, we did some review that this alarm signal should not have this kind of unstable state, because we can fix it to 0 or 1 by adding a threshold here. And in our paper, actually, we argue that the leakage here is not from the design miss by connecting the AES circuit to the alarm signal. It's I didn't explain, but this alarm signal becomes high when he detects the current. Actually, this sensor detects the current inside this chip. So by doing laser injection, it will generate some irregular current, and by combining it with AES calculation current, then when it's higher than a threshold, this alarm signal will become high. So we consider this leakage comes from when we set the laser injection to be a critical part phase where it become high or low or very unstably, then the AES calculations current will become affect to the alarm signal, whether it's become high or low. Since the laser photon injection, laser part is stable, the AES is varying. So the alarm signal varying is affected by the AES variation. So that's our understanding. Okay.
Got it. Yeah. Makes sense. So then I think, it's probably not so much about the physical design in the chip, but maybe even the board level, maybe some more decaps should be used. Or anyway, I mean, I think it's a very good point that whatever countermeasure you have, what you think is secure and makes sense, even at the system level, when it comes to actual physical implementation, there are so many ways which, where things could go wrong and which an attacker can leverage. Yeah.
Yes, definitely this alarm signal could be implemented in a better way, so this kind of attack become more difficult. And also, actually, this work is not actually an practical attack, because usually this alarm signal are not accessible by the attackers. So we're just doing some tests and we find some interesting result. That's all. Thank you.
Right. And I mean, if you don't mind, or the moderators don't mind, I also got another question.
Okay. Yeah.
So, I mean, due to lack of time, you didn't really talk about the threshold implementation too much, but I would still be interested why you think, there might be some possibility to attack this. So I understand you can't prove this, and I also understand it's difficult in practice. But I'm not really familiar with the details of the implementation. So I'm just curious about, your intuition or your thoughts, why you think it could still be attacked.
So I suppose that you know some details of threshold implementation, and
not so much, unfortunately. So I mean, I know the scheme in general and what it's used for, but I didn't bother about actually way how it's proposed in the details now.
Okay. So I'm trying to explain shortly, but actually it's quite difficult. The basic idea is that so here's 3 shares of input of x1, x2, x3, and this is 3 calculations and 3 shares of output. The idea is that if you only observe one calculation, G1 or Y1 here, you cannot understand the information of X, original information of X. This is definitely. So in the work of one that it tried to explain that TI is secure against FSA, it tried to say that if the circuit is fixed and we give input, then the critical path is actually decided, one of the calculations of G1, G2, G3. Then by doing FSA, the attackers can only get information about one of these 3 calculations, either G1, G2, or G3. Because you can only observe one calculations information, you can never get the information of X. So that's the idea. But in paper 2, it says the assumption is actually not correct, because although the original X is fixed, but these 3 shares are randomly generated in every execution. So that for every calculation, X is fixed, but X1, X2, X3 is not fixed. So the critical path in every execution is actually different. It could be G1, it could be at G2, it could be at G3. So by doing FSA, you are trying to, every time you're trying to measure the leakage information, but actually you are not measuring only one calculation, you are measuring all 3 calculations. So theoretically, by doing FSA, still you get the information of all 3 calculations. So if we do some properly statistical analysis, we can recover secret of X. That's the theoretical proof that it's not secret, properly secure. But the problem is that if we're doing the real attack, you don't know which one you are measuring, and you don't know what's happening. So you are doing like it's too many randomness, too many uncertainties here, and you're trying to observe some only the information you can observe is just 1 bit, but there are so many possibilities here, and you're trying to do some statistically work to recover it. And considering X1, X2, X3 are all 8-bit values, so there are too many combinations here. So actually, it's quite difficult. You have to do so many measurements, so that's quite difficult in my understanding.
Got it. Yeah, makes sense. I mean, I don't know, the moment you have a lot of measurement data, maybe if you try to do some machine learning, maybe then even any subtle leakage or correlation you could still infer. But yeah, I see the point. Yeah. Thank you very much.
We can make some toy TI implementation and try to do some tests maybe. But if it's in a real AES, that's quite difficult to start.
Right. Yeah. Thank you very much. Yeah.
Thank you very much.
So any more question from the participant? So if there is no questions, then thank you, Dr. Yang Lee, for your nice presentation. He has discussed many things about that. He's discussed side channel attack, fault attack, shape error attack, and so on. So that is very nice presentation, Dr. Yang Lee.
Thank you very much. We're glad to
Thank
be
you.
here. Okay.
So see you again in near future.
Okay. Thank you.
Okay. So today's next speaker, Dr. Susmita Ruj. She is an assistant professor at Indian Statistical Institute, Kolkata, and senior research scientist at CS Euro Data 61 in Australia. She received her BE degree from the Indian Institute of Engineering, Science and Technology, IIES Disipur, India, and Masters and PhD from Indian Statistical Institute, India. She has an assistant professor at the Indian Institute of Technology, Indore. She was visiting researcher at NTU Singapore, KDDI and KDDI Research and Development Labs, Japan, University of Wollongong, Australia, India, France, Kongshu University, Japan, and intern at Microsoft Research Lab, India. Her research interests are applied cryptography, data privacy, cloud security, and so on. Susmita served as program co-chair for IndoCrypt 2019 and CCS workshop series, blockchains, cryptocurrency, and contracts, ECC. Now she will speak today proof of storage and application on to blockchains. So Dr. Susmita, you are welcome to start your presentation. Hello. Dr. Susmita, you can start your presentation.
Can you hear me?
Yeah.
Yes.
Okay.
Yeah.
For some reason, my camera is not working, so I will just be speaking. Thank you very much for inviting me, and also for the nice introduction. So what I'm going to do first is share my talk, and then we'll. Okay. Oh. Um,
Dr. Participants,
Due to some network problem, ma'am will be joining very shortly.
sorry
So
about it.
we are waiting for ma'am.
Yeah.
Ma'am has
Sorry,
joined.
I don't know. There was some problem. I'm going to share the screen, and can you see my screen now? Hello, can you see my screen?
yeah.
Okay.
Okay.
Thank
Yes,
you very
ma'am.
much.
Yes, ma'am.
So I'm going to talk about proofs of storage and application to blockchains. So before I start, I will say that I simply don't like talking online. The reason is that I am not able to see my audience nor interact with them. I think it's very crucial for any kind of technical presentation where you actually can actually modify your talk depending upon the looks on the audience faces. And I apologize if I have not been able to make things clear, because I'm not being able to understand how everyone is perceiving this, perceiving as things as I'm talking. But still, I'll try to, just go with the flow. So typically, I would expect my audience to also ask me questions in the middle of the talk. And even if I don't finish the talk, it's okay. But, if you have any questions, please feel free to just, stop and ask me questions, and please speak up on the microphone if you think you have a question, because that can actually make things easier. So the part of the, mostly what I'm going to talk about is driven by a couple of applications. And one of the main concern nowadays is about data sharing. And we have recently heard many data breaches, and also various scandals regarding data sharing. For example, the Cambridge Analytica scandal, which actually brought in a number of questions about how various organizations or where we share data are handling this data and what they are doing with that data. And even without such big news, we can still imagine that whenever we are sharing data with third parties, we do not have any proper guarantees that that the data is safe out there. And one of the ways to protect our data is to use some legal sort of mechanism, and that is why GDPR and other the California Data Protection Act, these have, or even the Indian Data Protection Bill, these are trying to safeguard the interest of users. So today's talk is going to be about data storage and sharing, where I will talk about proofs of storage and blockchain-based audits. I will touch upon data marketplace and talk about a few challenges that we face in data sharing and how we could possibly solve them. So often data that we store can provide long-time, we would require long-time reliable storage, because the servers can, discard old data and hide data loss. So if data is deleted, then we might not have any way to recover it. Therefore, the client needs a guarantee that the data is stored with third-party service providers correctly, and it is not tampered with. What we require more is that it is not even shared with other parties without our consent. There is this I just talked about the General Data Protection Regulation, which came into force in the European Union in May 2018, and the main purpose is to protect data, protect users from various types of data misuse, and guarantee protect data integrity, or take some measures to guarantee data integrity, accountability, data accountability, and also enable that data is properly shared with parties, protected against data breaches. And in order to do this, there are various ways, various requirements. For example, data should reside in a particular geographical location. And there is also another clause, which I will not be talking about, which is the right to be forgotten. So to talk about, just like we do audits of various information, this data auditing is also quite an important thing. It means many things, and in this talk, I will actually focus on only a few aspects. So it could mean that data, audit is also done to assess the quality and utility of the data. And in order to do this, we need to ensure the security, data integrity, protect the privacy, and so on. And if you think in the terms of in a broader context, where even if we do not think of the technical way of dealing with this problem, is to deal with how do we store and use data, whether we have a proper consent in place, whether this consent is being abided by, whether there are if there are any ethical implications, is it being taken care of, and if there is some requirement on the place of storage or the geolocation, it is being addressed properly. So all these are things that an data audit should actually do. And it should also try to protect against data breach in case there is one. In this talk, we will talk only about how to protect the data integrity and protect against data breach, or give some protection against data breach. But we will not discuss about other features. For example, can we say that whether the data has been stored in a particular location? Because if you think in a very simple terms, if you think in terms of data being accessed by the, if you try to figure out if by the IP address whether the data is in a particular location, there is no correct way or guarantee that you can do so, because the IP addresses could be spoofed and so on. And over here, I'm talking about proofs, because these are like really mathematical guarantees. And why are these important? Just like you go to the court of law with some evidence, and then you ask the judge whether you actually try to build your case. This is also a scientific in the scientific community, we try to build our case by giving proper mathematical proofs. And these are just rigorous evidences. It's not just evidence, it is like a very, very, very scientifically designed way of proving that what you are actually claiming is correct. So that is why the concept of proofs in data storage also becomes quite important. And in this talk, I'm going to talk about how we do so. The other thing we are going to talk about is to protect against data breach, because we have seen even there have been very high profile data breach cases. For example, we saw a couple of years back about the Aadhaar data breach, and there were some other breaches like Equifax and so on, Marriott. And the GDPR, Article 32 of GDPR and 34 of 34 also say that that the personal data should be pseudonymized and encrypted wherever possible, so that personal data is rendered unintelligible to any person who is not authorized to access it. So this means that if you try to use some techniques like anonymization or encryption, it will deter. I mean, it is not like that could still be data breach, but you might not be able to. You have to do it in such a way that even if there is a data breach, the attacker is not able to get valuable information about the data. So first I'll talk about, quickly talk about the problem of protecting against data breach. I'm not going to talk in very big details over here. And one of the ways to do so is to do encryption. The main challenges in this case is that whenever you share data, it is not just the data that you are sharing. It comes with a couple of other things. So for example, you would like to do some analytics on that data. You would like to, do some data, answer certain queries, any kind of data retrieval. And at the same time, you would like to do this efficiently and with accuracy. So all this makes things encryption a challenge for addressing when you try to do data sharing. And there are very well-known techniques of homomorphic encryption where you want to compute on encrypted data, the encrypted search, searchable encryption to search on data, and various access control techniques that are available. And these come with their own challenges when data becomes large and when there are complicated operations to be done. So we are going to talk about proofs of storage, or how to protect the data integrity, and give some formal mathematical guarantees that yes, the data that is with some outsourced server is actually intact. So let me just start with some very simple ways of doing it. And the first way is that if you try to think of the data being divided into blocks or chunks of data. So suppose you have n blocks of data. So you could essentially, the data owner could essentially store all these information. You could store all these information in the outsourced server, and sometimes you would send the random indices and say, like, give me, try to keep certain data with yourself or the data owner. So for example, the M1, M2, M4 and M9 blocks are kept with the data owner. And then you make some random queries, like ask whether the first block or the fourth block and the ninth blocks are intact. And by verifying with the data that you are storing at your end, you can say whether the audit has been performed or the data integrity is protected or not. So over here, what we see that the data owner still has to maintain a copy of the data. Some of the data, if not all. And there has been, the traditional proofs of storage, and these are mostly two classes, which are, pretty much old concepts, but recently these have been revisited in new light and being studied. One of the concepts is a reprovable data possession, or PDP, and the other one is the proofs of retrievability, or proofs of where you can not only give a guarantee that the data is stored, but you could also construct it if there is some erasure to a certain extent. So the first thing we talk about is the proof of data possession, and where you have, say, multiple blocks, as I mentioned. And what you do is that apart from this message, you also have some authentication tag attached to that message. So you upload the message and the authentication tag pair to the database, to the outsourced, to the server, for all the n blocks. And when you try to try to pick up some random indices and try to query some of the blocks, the data owner receives the corresponding message, the data block and the signature, and it simply verifies, not the signature, I would say the authenticator, and it simply verifies that this sigma I is the correct authenticator for MI. Note that if we have a private verification where the data owner is the one who is verifying, then we would typically use sigma, which is a message authentication code. If we have a public verification, then sigma would be a signature. And in the case of proofs of retrievability, what happens is that you have a file which you can possibly erasure code and upload the erasure coded, and then you divide it into, then you upload all these message and all these blocks with their authenticators. And note that here again, if you try to do the same thing, the random indices, you simply can verify as before whether sigma is a correct authenticator for MI. Now, what happens is that the private verification, again, you simply use message authentication code. For public verification, you use a signature. Note over here that one of the things to take into consideration is that when you try to give such proofs, these proofs are short and concise, or I would say succinct. In this case, it is simply in the order of the number of indices that you query for. So it is ideally would like it to be a constant and short. But over here, you see that it depends upon the number of indices that you have queried for. So this is something that we would like to minimize. So proof size is proportional to the query size. Now, there is one more thing to keep in mind, that when I set public verifiability, we mean that there is a dedicated auditor. It is not the data owner who is auditing, but there is a data auditor or who is doing this verification. And in most cases, you will see that there is a third-party auditor who is providing the service. And in this case, one of the requirements is that not only will the data auditor be able to verify that the proofs are correct, but it should be possible to do this without knowing the blocks. In the case where I just mentioned, in the two cases that we saw before, the auditor comes to know certain blocks that it queries, and this might not be a good option if we think of privacy. So again, repeating the requirements of an auditing scheme would be like, the verification should be fast, proof should be short. Anyone can verify. The third party performing the audit should have no knowledge of the data, that is privacy preservation. And naturally, people started asking this question long back, and there was a very elegant solution which was there was an elegant solution given way back in 2008, followed by 2012 Journal of Crypto paper by Sheckham and Waters, who said that, irrespective of the size of the query, you could get some very short proofs. And the way they do it is that they try to aggregate all these message and try to generate a combined message and a combined authenticator in such a way that the combined authenticator would be a valid authenticator for the combined message. And if this would actually be valid only if all the messages and the authenticator are a proper match. So this particular technique was very useful, and it has been widely used. If you look into the protocol, I have written something. You don't have to read everything over here, but the main idea is that to do this in a private auditing case, you simply use some PRF, and in the public case, you rely on a more advanced mathematical structure called a pairing, called bilinear pairings, in order to do this. So note two things over here. The two things to take away over here is that the proofs should be short, irrespective of the size of the query, and ultimately that is the main concern, like how short my proofs are, how efficiently these proofs can be constructed. And it is not for this case alone of auditing. You'll see this theme recurring again and again in various types of in various types of models where there is a prover and a verifier. So the other thing to take back home is that even if we do not go into this detailed construction, is that the concept of linear homomorphic authenticator. at this point, just understand, I mean, if you have not, you're not, familiar with this sort of a work, that, as I mentioned, that this particular technique can actually help to get this constant size proofs. Now, what I'm going to do is that talk about one construction that we provided some time back, and this is about the dynamic auditing scheme. Look at the challenge first in the dynamic case. Dynamic means that you could modify the blocks of the message, or you could add or delete message blocks. So think of the very simple case where you simply want to modify this fourth block. So what you can do is that you have to, if you want to modify this the fourth block, you also have to modify the authenticator. Now, what happens is that the server, instead of modifying this information, it can still keep the stale block M4 and the stale authenticator sigma 4. And if the data owner or the auditor tries to queries the fourth block, it can give the old result M4 sigma 4, and it will simply pass the result even though it had not modified the block. So you understand the problem, that the problem is that even with the stale information, it can pass the audit, which we do not want. So yeah, so this paper actually was with my student Binando, and it appeared in 2016 Asia CCS, and the full version has been accepted in transaction on cloud, yeah, TCC, yeah. We also have an archive version in case you want to have a look at it. So note that this technique will work only if the server sends this updated proof. If you notice that at this stage, when this updated data is sent, the server should send the proof of freshness that, look, I have updated it, some sort of a proof for update. Else it will return old results. So this is the whole crux of the story. How would you send a proof of update and how you would verify it? So you have to guarantee that the data is fresh. Naturally, the question becomes, what is a proof of update and how does it look like? And in order to do this, we would like to maintain some data structure so that when the block is modified, in the data structure, the tag is also modified, and this information at the server end are done in such a way so that this would be an efficient update, and at the same time there would be some proof that the server can generate in order to prove that yes, the data has been modified correctly. And one of the nice things to do is, one of the challenging questions first is that what does the data structure look like? And if the data was static, then Merkle trees were a good option. An alternate data structure is a skip list. And we designed the paper that we talked about uses this ranked-based skip list in order to do this. So I'm not going to talk in details because of the time constraint. I don't have much time, I believe, and because I will talk a few things about other problems as well. So a challenge is always like, I'm just going to skip this, but it also means the same thing. Like if I want to, this is about if you want to insert a new data, the main challenge becomes then, if you want to insert a new block M4 then M5 onwards, it's like pushed one place further. And then the whole idea of constructing the authenticators become a little bit complicated, because many of the authenticators are, when they are constructed, they have the index as a function used in this construction, which makes it very difficult to just upgrade or change a normal static proof of storage to a dynamic proof of storage. And that is what the research is about. So the research, from the research perspective, it is even from moving from the static to the dynamic case, it is like a non-trivial amount of work, and new concepts applied, used for these for the dynamic case. And one of the things that we did was use network coding technique in order to do this. And I'm going to just give a very high level overview of the things. So what we do initially is that we we first send the data, and later what we do is that when we initiate an update. So for example, I'm trying to do an insert after the ith index. I try to construct a proof, the phi I, which says that yes, the data has been properly inserted, and this is done using the skip list. I update the skip list as well. And naturally, if the data owner first verifies that this update has been performed correctly, and only then can it start doing its challenge response in order to figure out whether the integrity has been protected or not. So there is a whole lot of math involved here, and I'm going to skip it. Result-wise, we actually compared with one of the state-of-the-art at that point, where which actually gave some very interesting results compared to even the static storage. So this SSCS, this appeared in Infocom 14, and this was some of the results that we did in the Asia CCS 16 and the recent TCC versions. And it shows that we get considerable, similar types of storage overhead compared to the static scheme, but it is a whole lot of improvement, because we have being able to move from a static to the dynamic version. On the other hand, we see that you will see that for the from the computational perspective, the static scheme is quite inefficient, because they were using a whole lot of other techniques to do it, whereas the technique that we used was far more efficient than theirs. And so we not only got a better improved dynamic scheme, but also it was much better compared to the computation overhead for the static scheme, and similar communication overhead as the dynamic as the static scheme. So I'm not going to talk too much in details about this. So this work actually appeared in the Transaction 2018 with a dynamic POR scheme, and it was because of some nice efficient construction using certain data structures. Not going into this. And the last part, or I think I have not too much time left. So what I'm going to do is that what it means to is that all that we want, and why does why I said that I'm going to talk about blockchains in this talk. So natural question comes like, why do we need a blockchain? Why am I trying to use a blockchain? And this is a question I always ask when I'm trying to design a blockchain-based solution. Just to reiterate for people who are not familiar with this literature, is that a blockchain is simply, immutable, verifiable, distributed ledger, and it's the very simple structure. Blockchain could be realized in various ways, and one of the ways it is realized is using a linear structure, where each block is linked to the previous block in such a way that if the previous block changes, then the whole and then all the subsequent blocks have to be changed in order to have to be changed. Now, if we had maintained only one copy of this linear structure blockchain, then it is all good. So you change one transaction over here. Say if you change TX1, you would essentially be able to change this whole thing, and you could subsequently change all the other later blocks in the blockchain. But since this blockchain is maintained, the same copy is maintained in various peer nodes. If you change one copy, you have to change, say, thousands of other copies, which is not possible if all the people who are maintaining these copies are, at least the majority are honest. So why do we need a blockchain in the first place? And what was, where were we stuck over there? And where were we stuck in the previous proofs of storage? Now, when you think of proofs of storage, there are quite a few things to keep in mind. So in the first case, we were assuming that the client is honest and the server is dishonest, and it is the server who is modifying the data, and the client is not. The client is all good. Now, think of it in this way. If we want, say, okay, if we want to if suppose, let me just move. Okay, we were here. Okay, if we want it other way around, where even the client is dishonest, then it becomes, quite a bit of a challenge, because, and why will the client be dishonest? The client could be dishonest because it could get financial benefits if it were able to correctly frame the storage server. So if both the parties could be honest, then there should be some other reliable party who could actually, or honest arbitrator who could actually figure out who is actually honest and who is dishonest. This is also the proof of storage is also one of the building blocks of data marketplaces that I will not have time to go through. Then we have a peer-to-peer storage, which are very popular nowadays, with some of the proposals like Filecoin and StoreJ being used. We also developed one with the researchers from KDDI R&D Labs Japan, which we call Blockstore. And it has also been used in proofs of storage like Permacoin, Chia, and Spacecoin. So this is the whole scenario. Now, this is a case of a dishonest client. So here, the client could be dishonest, the server could be dishonest, and even the auditor could be dishonest. So if you think of two dishonest people, potentially two dishonest people, like the data owner and the client, the data owner and the server, then someone has to be, like, you go to a third party who is often the court of law to get a correct or get a fair verdict. And here, this court of law, or the trusted party is being, the role of the trusted arbitrator is being played by the blockchain. And we assume that whatever blockchain is in place, it is a secure design and it is trustworthy. Now, imagine that we have now three parties. This is the data owner, this is the client, and sorry, this is the data owner, this is a server, and this is an auditor. And we could, the way it goes is that initially when the blocks and when the blocks are stored on the server, the signature, the blocks are signed, and signed by not only the data owner but also the server, and this information is kept in the blockchain, so that none of the blockchain, none of the data owner or the client, data owner or the server can actually retract later. And what happens is that later, after this step, the data owner deposits some money because it has to pay the server for storing the data. The server also deposits some money in case it actually defaults. Then it will send this money back to the, it will pay the penalty to the data owner. And the auditor, to protect the auditor from being to protect the auditor from sending malicious, sending very specific type of queries to choose the indices. This query set is generated randomly, with the randomness being generated from the blockchain itself. And then what happens is that the proof of storage is obtained similarly as before, and it is verified. Note that if the verification is successful, then the payment is made, else there is a penalty involved. Now, what is the challenge over here? And what are the things that we address is that if we actually prove that if there is a data owner, if the data, at least two of the parties are honest, then this is going to be, this protocol will be correctly executed. Now, we could essentially reduce the cost of multiple audits by clubbing together the audits from multiple that is done multiple time, using the concept of state channels, and this makes it more efficient type of a construction. We do have some interesting results over here, and these were done on various types of file sizes, and we see that the blockchain verification time is the proof verification time by the auditor is much smaller compared to the blockchain calls, which is actually something that we had also guessed. The other thing is that if we look into the sorry, the results here for the owner computation time. The owner computation time is much higher compared to the time for computation after we club. So this is on the right hand side, you have the results after you use the state channel optimization, and this the left hand side actually gives the raw or the vanilla type of a construction. And we see that the time for computation has been drastically reduced in this state channel type of a construction. So what I'm going to do is that I'm going to stop here. I mean, I'm not going to stop here. I mean, I'm going to stop the main most of the, I'll just talk a little bit about some of the challenges here and that we are essentially working now. So I'm going to skip these slides. Just mentioning that data marketplace is a very good, nice example where we have buyers and sellers, and these sellers essentially take this data from the data owners and sell it to buyers, and we have to ensure that through the data market, and we have to ensure that there is a fairness, meaning that the sellers get whatever they should be paid for, and the buyers receive the content as they should be able to get, and no one is cheated. And this can also be done using the blockchain. And I'm not going to talk in details about this, but you can refer to our paper. So going beyond this data audit and data trade, as I mentioned, is that you need a lot of other tools to make a whole lot of working system. And some of the things that we work in this particular thing is also some data analytics on encrypted data, where we have done some work on encrypted graphs, and with my PhD student, and some work on searchable encryption with collaborators. We have looked in the past. We have worked quite a bit on access control techniques, and these are also important. The reason being that nowadays there is a lot of stress on having proper consent and access and authorization. So it's just way of scientifically enforcing all those that the legal rules or clauses demand. The challenges, I believe that one of the challenges that we have now is that there are certain legal requirements, and translating them into like automatic translating them into statements which can be automatically executed using the smart contracts that can be deployed, smart contracts that can be deployed in blockchain or otherwise. This is something that that is very essential and is nowadays a very hot research problem. So I would say that codifying law is something that can be considered for PhD students here. It can be considered as a very challenging open, not open problem. People are already working on this quite a bit now. The other thing is that when I talked about the prover and verifier, this is actually some of the it is a very it is a protocol which is very widely used in various other types of proof systems, and and these are widely used in zero knowledge proofs and various other authentication mechanisms. So even for the efficiency that we achieved, we could still think of it that these are pretty slow. So how do we improve on that is one of the questions that we have. Some of the things that we are interested in to pursue is a proof of replication in the cloud, dynamic search, verifying search, and so on. And in the blockchain space, these are some of the recent researches that are happening elsewhere. And there is a very good mix of both these two directions that are worth pursuing. So with that, I will end my talk, and if you have any questions, you can ask me. Thank you.
So participants, you can directly ask the question, or you can put the question in the chat box.
I see that there is a question. Difference between proof of work and proof of stake. Okay. Yeah. So typically, proof of work essentially is where you do a non-trivial amount of work to prove that to solve a difficult challenge. And some of the blockchain constructions like Bitcoin and all, they use proof of work. So ultimately you have to create a block. The miners have to create a block, and there are different ways in which you can add the block, and you have to add the block in such a way that everyone can agree that yes, this is the block that is the correct one. So if you put one block and the other person puts another block, there has to be some mechanism of actually kind of deciding which block goes into the blockchain. And so proof of work is one way of doing it. Proof of stake is another way of doing it. In the proof of work, you say that, yes, look, I'm going to put a block, I'm going to solve a problem, a difficult problem. And in doing that, solving that difficult problem, I have to do some non-trivial amount of computation, or the proof of work, that is what is called. In the proof of stake, the winner is the one who typically has a higher stake in the system. It means that, for example, it is just intuitively, it is something like, if I have higher stake in a system, higher stake, I am more likely to do something honestly, because if the whole system collapses, I will be the one who will lose, right? So this is a main whole what would I say, like a whole broader idea of proof of work versus proof of stake, and there are different ways to construct these. Did it answer the question that you said? Okay, and the other question that I see on the chat is that what is the scope of AI and blockchain? Well, there is a big scope. Now, one of the things is that AI for blockchain, and I would say that there is a lot of scope. So, for example, there is a lot of artificial intelligence techniques that are being used to analyze various types of, to get a better understanding of how blockchains evolve, how blockchains, the transactions are look like, or the getting some pattern about who are transacting and how much volume and so on. Another class of problems is that blockchains are typically being Bitcoin. I would not say blockchains, but I would say that mostly the cryptocurrencies are also nowadays being used to collect ransomware and so on. So AI techniques are also used to address this problem, to find out, gain certain insights on this. So, and on the other side, people can think of blockchain in various ways in AI, like, whether if there is some decision being made, whether this decision is being correct and it is fair, and because many things can be recorded on the blockchain, and by using this information, which is non-retractable, you can figure out whether whatever you had claimed to do, you are doing exactly that. I think this is something that I think I've addressed. The research idea of convergence, according to, yeah, this is something. I mean, people are both working from both the directions. Yeah, and there is one more question about the UTXO model and the account-based model. So typically, what happens is that the UTXO is like, it is of this type that, you have the transactions being made, and it's like something like in our wallet. That's what you exactly do. You have, say, 5 rupee note, 10 rupee note, and so on. And when you are paying someone, you simply say 25 rupees. You do not give, you do not just take a note and just 50 rupee note and just half it and give it to the person, right? And this is exactly what UTXO is all about. Like, you know, you look into the wallet, you try to see if you want to pay 25 rupees, you can pay 10 rupee and 5 rupees, or you could pay 20 rupees and 5 rupees. So unspent transactions are what is you have in your wallet, and from that wallet you give it. And the Ethereum based model is a little bit different, where it is like, it does not work in this way. Like, you do not have it, and it is as if you do not maintain these UTXOs, but you just do kind of a balancing when you make the payments. I don't think there are any more questions. So if there are questions, you can always reach me out on my email and ask me.
So participant, any question is there, you can directly ask.
Yeah, I think it's good. You know, we are already making the other speaker wait.
Okay. So thank you, Dr. Susmita, for your valuable talk.
Thank you very much.
Nice talk. And you see, even you see, I talked that Abhishek also, few days, Abhishek also given talk in our one workshop. He also talked about you. I also know you. And Professor Bimal Rai is also given that on the first day.
Yeah.
So
it's a very nice you know, group of people that you have been able to, researchers around the world that you have been able to assemble. That's really, you know, I'm pretty sure that the audience is benefiting from all the lectures. Thank you very much.
Thank you very much.
Thank you.
So okay, thank you. So our next speaker is Professor Rakesh Verma. Rakesh Verma is currently a professor of computer science with the University of Houston, is USA, where he is leading a research group that applies resource reasoning and data science to cybersecurity challenges. He is the co-author of Cybersecurity Analytics CRC Press 2019, which discussed key data analysis techniques and their adaptation for the cybersecurity challenges. He has co-organized the first anti-phishing shared task in 2018, and he is the Fulbright senior specialist in computer science, panel chair of ACM CodaSpy 2020, and PC co-chair of ACM CodaSpy 2021. So now I request to Professor Rakesh Verma, you are most welcome to start your presentation.
Can you see my slides? Thank you, Debashish, for the nice introduction.
Yes, sir, it is visible. Yes, sir, it is visible.
And so let's get started. So after that very interesting talk by Professor Roj, now we are switching gears a little bit. We are going to be talking about data science for cybersecurity. And, you know, I'm taking the liberty of sharing some of my experiences along with the research that we have been doing in the REDAS laboratory. REDAS stands for Reasoning and Data Analytics for Cybersecurity. And this research is supported by the National Science Foundation and the Army Research Office. So let's get started. This is the library of a school somewhere in used to be called Madhya Pradesh, but now it's Chhattisgarh, I guess. And from this library, you know, a student checks out a book whose title is Robinson Crusoe. Has anybody, you know, ever read this book or even heard of this book? You can unmute yourself and let me know, or okay. Everybody is very shy today, so let me continue. So this book was actually a very popular book, at one point of time, and maybe still is. Yeah. So sorry, somebody said something. Okay, so let's continue, and then now we are switching. I'm not able to hear.
Sir, can you make it in slides view?
Debashish, are you saying something? Okay, yeah. So
No, I'm not
possible, please
saying.
make it in the
that
slideshow view.
Akash and
The slideshow-
somebody else also said that they've read this book. Okay, so let's continue. So time passes, and many years pass actually, and then there is this phone call. Suddenly, one fine day, I'm sitting in my office, and on the other end, there is the professor from English department, whose name is Irving Rothman. He's not with us anymore, unfortunately. Professor of English and scholar of 18th century British literature, the thorough gentleman. I miss him very much. So he was on the line, and he said that there is a great controversy about the works of this author. And guess what? This is Daniel Defoe, the author of Robinson Crusoe. So, immediately when he said that there is this great controversy about his work, so, I got interested. And he mentioned that, there is a professor from Indiana University whose name is John Robert Moore, and whose career actually dealt with Defoe a lot, right? So, 55 of his 150 odd research papers and articles deal with Daniel Defoe, and his best known books are Daniel Defoe, Citizen of the Modern World, and a checklist of the writings of Daniel Defoe. So, it was Professor Moore who established the Daniel Defoe canon, the list of works that are attributed to Daniel Defoe. But then what happened is that after Moore's checklist of writings came out, right, two professors at Oxford University, Owens and Furbank, okay, on the left you have Owens and on the right you have Furbank. They went through the list of works of Daniel Defoe and eliminated about 250 or so out of a total of around 520 or 530. So about half the works, right, they removed from the list of writings of Daniel Defoe. And why did they do that? They did it on subjective grounds, right? They said that, okay, we don't think Daniel Defoe thought like this, or he couldn't have gone to this place, and so he couldn't have written about it, and so on. So Daniel Defoe actually was a very prolific guy who wrote lots of books, articles, newspaper columns, and so on, even pamphlets he produced. And, at various points of time, he had a very interesting and checkered career, including being a spy. Okay, so you should read about Daniel Defoe. It's a very interesting, about how his career kept changing and going through various phases. But he wrote a lot, and throughout his life he was writing a lot, and so that's why all these works came into his list and are attributed to him. So then, Dr. Irving Rothman, our professor of English at the University of Houston, he started scrutinizing their paper. And then he came up with this idea that, okay, I should look at these from the stylometric point of view, right? So he started looking at it from, Hargevic criteria, so-called. So Hargevic comes from Stig Hargevic, who did his PhD in Sweden, Stockholm University. And he actually looked at one of Daniel Defoe's works, okay? And he used manual analysis techniques, right? His PhD advisor had come up with some techniques of authorship style and stylometric analysis, and so he used those techniques manually to analyze a book by Daniel Defoe, and he considered whether it should belong to Daniel Defoe's list or not. Right. So Dr. Rothman took up Hargevik's PhD dissertation and started applying those criteria. And so he wrote this paper in the Bibliographical Society of America journal, right? And in about 2000. And he said that I'm going to scrutinize this paper of Owens and Furbank. And so began what we call the Defoe project, because he asked me if I'm interested in joining this project and whether I'm interested in using the computer to automate the process of analysis, right? So I was the student who had checked out the book by Daniel Defoe, Robinson Crusoe, and so that was still there in my mind, the very interesting book that he had written. And so I accepted this project, even though at that time I had no clue about stylometry or natural language processing. And I was working on actually equational logic, formal methods, rewriting, term rewriting, and so on. So this project was very interesting, and we gathered a very good data set of Daniel Defoe's works using first editions. It was a lot of work. Professor Rothman even went to the British Library, the famous one, where you have actually first editions of quite a few of Daniel Defoe's works and so on. So, and then we generated queries corresponding to Hargevik's work and so on. And then actually, that led to a lot of research in natural language processing, where we went from authorship attribution to identification of idioms and special phrases in English that have special meaning. For example, kick the bucket, right? So, kick the bucket can be a cow kicking the bucket when the milkman is trying to get some milk, or it can be an idiom meaning somebody has died, right? So how do you identify automatically whether a phrase has a special meaning? And so, we looked at all of these different problems, and we also got a Best Paper Award for our work on collocation detection, right? So again, collocations are special phrases. And actually, what I did was, when I moved from authorship attribution, I came to summarization and question answering first. And then later, I realized that some of the softwares that we were using for our summarizer, we have an automatic summarizer called SynSem. So SynSem stands for Combination of Syntax and Semantics. And so given a document, it will construct automatically a summary for you. And we also have MSynSem, where M stands for multiple documents. So you can give a set of documents, and our system will construct a summary for you. And the multiple documents problem is a little bit more challenging than the single document summarization, because you have a lot of redundancy when the documents are all related, they are on the same topic. Maybe there is a disaster, like for example, we had the cyclone recently, or the earthquake in Nepal or something like that. So there'll be a lot of repeated stuff written in very different ways, right? So the syntax will be different, but the meaning may be the same and so on. So a lot of redundancy. And we were looking at the these summarizers, and also we built this question answering system called SemQuest, which stands for Semantics Based Question Answering System. And we were participating in competitions that were organized by the National Institute of Standards and Technology in the US. So they organized these automatic summarization competitions and also question answering competitions. And we participated in those. And I was looking at the results, because what NIST does is they have human evaluators, not just automatic program evaluation, right? So there are methods for automatic evaluation of summaries and so on. There are not really very good methods for automatic evaluation of question answering systems. So they use human evaluators quite a bit there. And we were looking at the scores of our system versus human evaluators. So on a 5-point scale, the human evaluators were at 3.5. So even the human evaluators are given scores, right? So they are also evaluated. And so we were evaluated and we got a score of around 2.5, 2.6. So we were almost a full point below the humans doing the, question answering. And so I was wondering why we are so far behind. I mean, we do expect not to, compete with them directly and overtake them. But at some point, I think the future is bright. Automatic systems will come close to, beating humans in question answering as well. In chess and checkers and so on, they're already beating humans, the experts, right? So, we were looking at the reasons why our systems were underperforming, and then we realized that some of the primitives, some of the fundamental basic problems like named entity recognition, these are phrases, which denote names of people, places, things, etc. And so, we were using this Stanford Core NLP library for some of these things, and I started looking at them very carefully, their performance, and we realized that their performance, on topics or articles that they haven't been trained on is not very good, right? So, when you train on the data set and then test on a portion of the data set that you don't train on, they do, around 90% or so, but when you give them totally new data that they have never seen before, then their performance drops to like 70, 60%, right? And if you give them emails which are very noisy, right, lots of spelling errors and punctuation, that throws off the system, bad punctuation. So, then they even perform close to 50 or less than 50%. Right. So then I moved to the producer side and I said, we need robust techniques for some of these fundamental basic problems. And then we started looking at idiom detection, collocation detection, and so on. And anyway, so what's the connection to cybersecurity, okay, of all this? You might be thinking, right? So we switched gears at some point in 2011, right? So we started looking at the problem of phishing. And the problem of phishing, I'm going to talk a little bit more in detail about that. I'm sure many of you are familiar, probably all of you are familiar with phishing. And, we started in around 2011 on this problem. And then we published a paper in a conference in 2012, the European Symposium on Research in Computer Security, or ESORIX as it's popularly called, right? So that conference took place in Pisa, and that explains this picture. So let's move to phishing. From 18th century British literature, we are now moving gears and talking about phishing. So a popular attack vector for phishing is email, right? So, and emails, as you know, they propagate over the SMTP network, the Simple Message Transfer Protocol network, which is a logical network of SMTP servers overlaid on the internet, right? And the thing to know about emails, to understand what I'm going to be talking about next, is that emails have some metadata called a header, right? And it's a rich source of information about how the email, came from the sender to the recipient. And it also includes things like, for example, domain keys identified mail, DKIM, signature for email integrity, right? So this is authentication of the email that it hasn't been tampered with. And then there is also something called sender policy framework, right, which tells you about the authorized email servers in a domain. And so you can check whether, this email is coming to me from an authorized server or not, and then reject the email if the SPF record says that it failed this check. Now, you may not realize that the header that you see in Gmail or Hotmail or Outlook and so on is a very abbreviated header, right? So you actually have to go to the full email, the original email that Google, right? In Gmail, if you say show original, it will show you the full header email, right? And that has a lot of information. You should do that, right? After the talk, or, during the talk itself, you can take a look at a full header. And, when I teach the security course, I show the students the full header in class, but now I'm not going to do it. So I want to move to, how to solve the phishing problem with this background on emails. Okay, so we're going to talk about whether an email is a phishing email, whether a message, right? It could be a text message, it could be an email, whether it's a phishing message or not, right? And so we started this research in 2011, and as you can understand, our natural language processing work that we were doing previously came in very useful, because not only do we analyze the metadata, the header information, but we also look at the body text for clues whether this is a phishing message or not. So that's the connection of the NLP work with cybersecurity. And here is a sample of some of the phishing research that we did. And I call phishing a deceptive attack because it involves deception, right? The sender is trying to deceive the recipient into taking some action that's harmful. Like, for example, downloading an attachment or clicking on a link. So that's why we call this deceptive. And phishing also involves, besides deception, it also involves persuasion, right? So you have to persuade somebody to do something that is harmful to them, right? So they don't realize it, and so you have to deceive them to keep it a secret from them or hidden from them, and then make them do something. So it involves both elements of deception and persuasion. So the highlighted ones in green are the ones that I'm going to discuss a little bit more detail today. And if you're interested in any of the other ones, or if you have any questions from the talk, please feel free to email me, or in the chat, you can enter the questions today. So let's focus on phishing now, which is an acute and persistent problem. It has been with us for since 2004 or so, or even earlier, actually. There are reports of phishing around 2000 or 1999 even, from AOL and so on. And it can be used for stealing the user's digital identity or to install malware through attachments, right? So there are several newspaper articles talking about the millions that have been stolen via Trojans, and there was an attack on multiple banks with a spear phishing email and so on. And the estimates of losses from phishing range from about $200 million to a few $1 billion per year. And there is this organization called the Anti-Phishing Working Group, which keeps track of the unique phishing sites that have been created. And you can see that over the 6 months of 2020, this year, right, earlier this year, there have been, between 50,000 to 60,000 unique phishing sites created every month, okay? So this is an amazing number, as you can imagine. I mean, 50,000 times 6 months, we are already looking at 300,000 unique phishing sites, right? So take a look at their report on phishing. It makes for very interesting reading. And what is the modus operandi, right? The method of operation of phishers, right? Email is by far the most popular medium for phishing, but there are, of course, other ways like web forums, internet chat rooms, even phone phishing, right? And, using text messages for phishing. So voice phishing is called wishing nowadays, and SMS phishing is called smishing, right? So a lot of new terms have come about because of phishing on various kinds of media in social networks and so on. And so we are now going to look at phishing email detections. Here's a small example that you must have seen. Your webmail quota has exceeded the set quota and so on, and need to go here, and they'll give you a poisonous link, and you go to that link, they'll ask for some information and try to steal your digital identity that way, right? So you see in this that they are trying to persuade you to do something by claiming that you're going to be suffering some damage or loss, right? And then they give you a threat at the end that failure to do so may result in the cancellation of your webmail and so on, right? So this is an example of a phishing email, a classical traditional attack. Nowadays the attacks are much more sophisticated. So I began, as I said, in 2011. So I started tracking how many phishing emails are escaping from my spam filter. So I was using a spam filter that our system administrator had given me, and our university was also using a spam filter. So we had like 2 layers of filtering, right? And even then I had 115 phishing emails passed unmarked from my spam filter. So approximately 9 a month, right? And so you can see that it is a significant number, right? So about 1 every 3 days or so, 3 to 4 days. And I could be in deep trouble, at this rate of phishing, right? And so we started working on automatic phishing email detection. So we were reviewing the literature, and then we came across this paper by 4 scientists from Georgia Tech in 2008. And they said that it is non-trivial to distinguish phishing messages from legitimate messages, because phishing messages are constructed to resemble legitimate messages as much as possible, right? So they said it's going to be a challenge to automatically detect phishing messages, right? But we said, okay, we are going to work on this anyway. It is a serious menace, and okay, it's a challenging problem. So that's even better. It's not an easy problem to solve, right? So when we started, we said, what are the key principles on which we are going to base our phishing email detection, right? So we focused on the fact that the phishing email will require the recipient to take some kind of action. Okay, so that was one thing that we focused on. And then the other one that we focused on was that the phishing email will convey some kind of deadline or urgency. You have to do this within a week or so. And there is actually a very good reason why they give you this deadline, because if you look at the literature on phishing, you'll find that these phishing sites are generally up for at most a few days or a week, right? But some of them are actually quite long-lived. Okay, so a few sites escape from the authorities for quite a while. Okay, and so therefore they give you this deadline, because they know that their site won't be up for very long. Chances are bright that they will be found and shut down. Okay, and so the work that I'm going to be talking about appeared in Azorix 2012, and we use natural language processing techniques along with header analysis, and also we analyze the links in the email. Okay, if there are any links, then we also analyze the links. So we took a very comprehensive approach to the problem, and we created 3 different classifiers, right? So a text classifier, a header classifier, the metadata in the email, and a link classifier. So all the links are extracted from the email, and then they are analyzed for whether they are leading to malicious sites or not. And we called our solution Fishnet NLP. And the idea was that Fishnet NLP will be installed before the recipient, so that the recipient does not have to see this phishing email, right? So we can do the detection and put it in the spam box directly. Okay, and so we combined the results from 3 different analyses, right? So initially we said, let's keep it simple. We use majority voting, right, instead of some kind of weighted combination using probabilities and thresholds and so on. So we also came up with this idea of what we call contextual analysis. So, you know, the phishing that is happening in a context, right? Because there is all these emails that are sitting in the inbox of the recipient and also the sent box of the recipient, right? So if we can get access to those emails, then we can improve our analysis. And so we came up with this idea of context analysis, and we did some similarity, you know, and checking and so on. And in fact, we showed that context analysis does help improve the detection. So initially, when we started out, our database was fairly small. We had about close to 5,000 phishing emails that were available online. And then, you know, legitimate emails were a big problem because, you know, how do you find legitimate emails? And so what we did was we transferred the software, our detection software, right, to each one of the authors, and then we ran them on our own emails, you know, a random sample of our own emails. And so we collected together as a random sample of about 1,000 legitimate emails. And so here is a little schematic that shows you how things work for fishnet NLP, right? Then email comes in at the top, we extract the header from the email and give it to the header analysis, you know, a routine, and then we check whether the email is HTML, the body is HTML encoded or not. If it is encoded, then we decode it. Otherwise, we can give straight to the email parser, which extracts the links from the email and the body text from the email. And if it's HTML encoded, then we come through this path and then, you know, do the same thing. Then we combine the phishing scores using majority technique. And then I'm glossing over a lot of details today, you know, and going straight to the results. Okay. So if you look at the results, the very leftmost column, right? So this shows two different runs with about 4,550 phishing emails, right? And in this one, the first run is without the context analysis. The second run is with context analysis, okay? And this is the overall detection of the phishing email. This is from the header analysis. This is the link analysis, and this is the text analysis. Okay, and you can see that we are detecting, you know, at a rate of almost 98%, right, without context, and a little over 98% with the context. And you will say that, okay, the text analysis is lagging behind the header and link analysis, because both of the header and link analysis are, you know, above or close to 95, 96, 99%, right? And the text analysis in the 60s and 70s and so on. This is with context analysis, it's 77.1%, right? And so you might say, okay, why not just go with the header analysis and the link analysis? And the reason, actually, there are a couple of reasons for that. So one is that the header is partially under the control of the sender, right? Before the email leaves the sender's domain, right, they can falsify, right, put in all kinds of fake IP address, domain name, you know, sender name, all those could be fake, right? And then once the email leaves the sender's domain and comes to the recipient, in between it travels through several SMTP servers. So they try to avoid that by trying to directly send the email. So this is now considered a bad practice, and you know, more or less under control, this kind of direct routing. It's called source routing of emails. And so that's less and less, but still, you know, it does happen. And so you can see that relying on the header, right, when it's under control, partial control of the sender, is a bad idea, you know. So we don't want to rely completely on the header. So we try to look at the header information that's you know, after the sender domain, right? So we look at those things in our header analysis and try to emphasize, you know, the information that's likely to be correct. Of course, sophisticated attackers can also interfere with the email after it has left the domain, but you know, that's more difficult, requires much more technical knowledge, right? So this is for the phishing emails. And then on the legitimate emails, you can see the false positive rate in the bottom right corner. So we misclassify, I think, about 8 emails out of 1,000. And with the context analysis, 7 emails, right, out of 1,000. And again, the text analysis is lagging behind, but it's better on the legitimate emails than it's on the phishing emails. So we said that since the text analysis is not working so well, so let's improve the text analysis. And that led to the next work that I'm going to talk about. And so we wanted to see whether we can use statistical NLP techniques, right, for text analysis. And then we also wanted to see if we can use the natural language processing techniques such as part of speech tagging and word sense disambiguation and so on, because the same word can have different meanings in different contexts, like the word bank, for example. It can be a financial institution, or it can be the side of a river, right? And similarly, the word run and the word set have more than 100 meanings in English. So how do you determine what meaning a word has in a certain context? For example, the click, for example, is used quite a bit in phishing emails. Click on this link or click here and so on, right? So we decided to use statistical techniques combined with natural language processing techniques. And that led to a better text analyzer. And this work appeared in 2013 in the ICISC conference in Information Security and Cryptology. And a little bit about this research, how we do this. What we came up with is a semantic feature selection technique for text data. We analyzed carefully, some features on a small data set of phishing and legitimate emails. And then we tested on much bigger public data sets, which we didn't train on. And we did a detailed comparison of these statistical techniques versus the Azorix technique, which I call the intuitive approach. Okay. Now, we designed 4 different classifiers. And the first one was statistical pattern matching only classifier at the base of the pyramid. Then we combined that with part of speech tagging. And after that, we combined with part of speech tagging as well as word sense disambiguation. Our final classifier made use of this database called WordNet. So initially it was designed only for English, but now there is a European WordNet, and there is also a Indo WordNet and so on, which you can find. And so WordNet is a very nice knowledge base. It has all kinds of relationships between what are called syn sets, right? Sets of synonyms. So what WordNet does is organizes all the words that can denote the same concept into a syn set. And then it connects the syn sets using relationships like hypernymy, hyponymy. If you are unfamiliar with this term, then you can think of hypernymy and hyponymy as is a relationship, like, an elephant is a mammal, right? So elephant is a hyponym of mammal, which is a hypernym. So there are all kinds of very interesting relationships in WordNet that we decided to make use of, especially the hypernymy-hyponymy relationship. And now when we did our study, the phishing emails were the same as in the Azorix 2012 paper. But then the legitimate emails, we came across this Enron public email data set. And so we had a lot more legitimate emails now, right? So Enron was this company that went bankrupt around 2001 or 2002, something like that. And then there was a famous court case against the CEO of Enron and also the chairman of the board and so on. And because of this court case, which went on over many years, the emails of Enron Corporation were made public, around 500,000 emails. So we used a sample of 10,000 emails from the public Enron inbox email database, and also a sample of 4,000 emails from the sent mailboxes, right? A random sample from various users, different users. And then our training data set consisted of about 70% of phishing emails and the Enron inbox emails. And the test data set consisted of 30% of phishing, 30% of inbox emails, and 100% of sent emails, right? So that was a completely new test data set that we decided to use to see how our classifiers generalize to data that they haven't seen before. So here are the results for this. And the first classifier is actually the pattern matching one. And then the bottom classifier is the one which uses pattern matching plus part of speech tagging, word sense disambiguation, and word net relations. And as you can see, the detection on the phishing has gone up to 95%. It used to be around 66, 77%, something like that, using context analysis in the case of the Azorix paper. So we are doing much better. And the false analysis or the false positives from just the text analysis alone are around in the 2% range. But if we combine that with header analysis and link analysis, then of course this would come down much further. And so we did improve the text analysis. And so we were thinking about whether our methods will be enough, because so this is the question that we said, okay, are we doing everything we can to protect users? Because we are going to have some false negatives, right? And we are going to have some false positives as well. So this is one problem that we thought about. And then we started thinking more seriously about what we are doing. And we realized that data analysis or data science in cybersecurity is kind of special, because first of all, data sets are hard to collect, right? And they're also imbalanced. So they lead to what is called the base rate fallacy. And this is a popular term in security that you can look up. And then there is also the active attacker, right? The hacker who's trying to defeat all these techniques that people are coming up with, like, for example, the automatic detectors that I talked about. And so this has led to a whole new exciting area called adversarial machine learning. I will mention a little bit about that later, right? And so we talked about, we looked at all these problems, and we wrote this paper in the IEEE Security and Privacy in 2015 about all the essential data analytics knowledge that is required for security students and professionals. Okay, so then we started looking at the user side of the equation, because we said that we need to actually educate the user as well, right? It's not just enough to design automatic detection methods, because automatic detection methods will fail at some point, either because of a false negative, false positive, or because of the active attacker who's trying to defeat these techniques. So then we started working on what I call proactive security, right? And human factors. So we did this work on email masquerade attacks, where we did semi-automatic generation of emails in the style of two political leaders in the US, Hillary Clinton and Sarah Palin. So we took a real data set of their emails that's available publicly, and we used semi-automatic natural language generation techniques, to come up with new emails that we synthesized in the style of these two leaders. And the idea was that if we can synthesize new attacks, right, then we can subject our automatic detection schemes to new attacks and see if they can withstand or they can detect these new attacks, right? So this is why I call it proactive security. We are not waiting for the attacker to defeat our methods, right? We are generating our own new attacks and trying to see if our methods can survive those attacks, right? So we did a user study of our synthetic emails to find out if our synthetic emails are any good, right? So we did a user study in which we gave the users real emails of Hillary Clinton and Sarah Palin. So before they looked at, before they did the test, they had to go over the emails, the real emails, and familiarize themselves with the style of Hillary Clinton and Sarah Palin. And then we gave them a set of about 8 emails. 4 were real Hillary Clinton emails, 4 were synthetic. And similarly, 4 real Sarah Palin emails and 4 synthetic that we had designed. And then we asked them, can you tell which one is generated and which one is not? And how confident are you in your decision? What clues are you using, and what's your reasoning for your judgment or decision, right? And we also took some automatic authorship detection tools to see if they can distinguish between our synthetic emails from the real Hillary Clinton emails and so on. So we trained them on the real emails of Hillary Clinton and Sarah Palin, and then try to see if they can distinguish the real from the fake in the test set. And so we had some very interesting results that you can read more in detail about in this paper in Asia CCS 2017. And one of our very interesting findings is that people are more confident when they are wrong. Okay, and we also found that people cannot really distinguish. So the detection rate for humans in our study was around 52%. Okay, so pretty close to random guessing, right? And the authorship detection tools, the best one, we tried I think two or three tools, and the best one was coming up at 75% on one test set and a little bit lower on the other test set. Okay, so you can see that the semi-automatic generation of attacks is pretty good, and is able to fool humans and also able to defeat the automatic authorship detection tools at least some of the time, significant percentage of the time. And we continued this work further because we realized that Hillary Clinton emails and Sarah Palin emails tend to be very short, right? They're very busy people, right? So they write like 2 or 3 sentences at most, right? And so these are very short attacks that we generated, right? So then we said, okay, can we generate longer attacks which are still coherent and still can fool people? So we looked at job scams. Okay, so in a job scam, basically you get an email saying that, oh, you have been selected to be our customer representative, and we are this great company, in I don't know, some country, some remote corner of the world, and we need a representative for North America or USA or Canada or what have you, right? And so it's a pretty long email because it has a description of the company, what does it do, and what we want you to do, right? Collect, the money for the goods sold, and then you will get a cut of 10%, and it's all a scam basically, right? So we took a data set of, scams like these, and we also took real job offers that we, got from various sources. And we created, again, synthetic job scams, right? And so we did semi-automatic generation of job scams, which are longer and more complex than emails. And we also, said that, okay, let's see whether scaffolding, like, for example, sending the job scam through LinkedIn versus Gmail, whether it makes difference or not. And whether attaching a signature at the bottom or recipient name at the top and other clues like this, whether it makes a difference or not, right? So we did a large user study. More than 1,000 users participated in this study. And again, we asked whether they can distinguish the synthetic emails from the real ones, what is their reasoning, what kind of clues they focus on, and so on. And this paper was just presented actually this week, in Asia CCS. You can read about the details from that paper. A couple of very interesting findings that we got was that mobile users, right, are more vulnerable, because many of the users actually use their cell phones to do our study. And we found that there's a statistically significant difference between people who were using cell phones. Their detection rate was lower, and also the time that they were spending was also lower. And you can see more results and the kind of statistical techniques that we used in the paper in more detail. I will now move on next to Fishbench, which is a benchmarking framework that our group has developed, in which we are planning to release publicly in a month or so. And our goal is to actually compare and evaluate all the detection methods in a systematic and fair way, right? And make this comparison task and evaluation task easier for the researchers. Because right now what's happening is people are publishing papers, right? They have their methods, they have their own data sets, they have their own environment in which they run these detection methods on their data sets and so on. So there is no direct comparison, right? So what we said is that we need to design high quality data sets, and we need to do this comparison in a uniform architecture and environment. And that's when we can have heads to heads, apples to apples comparison, rather than, somebody is doing it on, I don't know, a desktop, somebody is doing it on a server, using different kinds of libraries, operating systems, data sets. Everything is so very different, right? And we also, used Fishbench actually to study the performance and the scaling of lots of different methods, lots of different classifiers, supervised and so on, deep learning included. And, those results actually are there in a paper in IEEE Access this year, which you can read in more detail. And then we said, okay, let's improve Fishbench so that it becomes much more easy to extend. So we use the Python reflection mechanism to make the extensions much more easy. And this is going to come in November. The paper on Fishbench 2.0 has been accepted as a poster at ACM CCS in November, and that's what we are planning to release soon. So this is the benchmarking work that we did. And so you will see that we went from phishing emails, and I skipped over the work on phishing websites and also links and so on. And then I talked a little bit about the user studies on email masquerade attacks and so on. And we also did actually a very thorough review of phishing literature that I'm going to talk about in a little bit more detail later. I mentioned the benchmarking framework. And what are we doing now? So now we are focusing more on deception and looking at a broader class of attacks, including fake news. Okay, so not just phishing, spear phishing, but also job scams, 419 scams, all kinds of different scams, as well as fake news. Right, so pretty broad class of attacks, which we call deception. So that's our latest project. Okay, so let me mention a little bit about the systematization of knowledge on phishing work that we did. So we said, let's take a look at the research literature. So we reviewed over 250 papers or so from 2010 to about 2018. And these included around 190 phishing detection papers, and the rest were studies about human vulnerability studies on phishing or spear phishing attacks and so on. And so the detection literature included phishing email literature, URL, website, and we looked at what kind of data sets people are using, how diverse they are, how recent they are, and if they are publicly available or not. So for the publicly available ones, we also looked at the quality of the data sets and so on. And we looked at the features people are using, the classifiers. We came up with lots of gaps in the literature, and also we listed a lot of key takeaways, right? And one of the key takeaways is that about 13% of phishing detection papers have considered security challenges seriously. Remember the active attacker, the imbalanced data sets, right? The quality of data sets and all those issues I mentioned, a little while ago. So it's really, depressing to think that there are so many papers, about 87% of papers, that are not paying attention, carefully to all these challenges in the security domain, And so we are trying to improve the state of the work in the field, by publishing this paper in the IEEE journals on surveys and tutorials. And this came out in 2019, 2020 as well. And we said that we have to educate people on data science applied to cybersecurity because it's special. And so, we came up with this book to help people. We call it Cybersecurity Analytics. And on the cover, we have a clustering algorithm that was run, on a malware data set. So it's very interesting that it came up with these very nice clusters in the data set that have been visualized with a software called TSNE. And that became our book cover. So maybe it's a good idea to show you the book cover in a little bit bigger, right? So that you can see it better. Right, so that's the book that came out recently, published by CRC Press, and it's available on Amazon India as well. And so we are trying to build the community, not just do research, but also build the community and make sure that higher quality research and higher quality data sets are conducted, are used and conducted, right? So with that, I'm going to wrap up, my talk. I don't want to take too much of your evening away. So here are some of the conclusions and the future work. So there's lots of interesting directions in natural language processing, phishing, deception, and so on. And there is much scope for work in security analytics or cybersecurity analytics, because remember that you can't just directly apply data analytics to cybersecurity challenges because it's a special domain, right? So you have to adapt the data analytics for cybersecurity challenges. And so there is a lot more work to be done here. And then you can take a look at some of the papers that I mentioned to dig deeper and also look at what are the open problems in the field if you're interested in pursuing research on these topics. And with that, let me conclude with a big thank you to all the organizers, and especially to Debashish, who's been doing a lot, and also to all of you for listening. And my contact information is on this slide in case you want to email me some detailed questions and so on. And also I've given a link to my web page so you can take a look at some of the interesting data sets that we have collected, as well as I have links to other data sets as well if you are interested in doing research in the field, right, on this field. So with that, I'm going to stop, and let me stop sharing the set of slides and see if there are any questions that are there in the chat. So there are a couple of questions. So first question that I see is, how do we collect authenticated data set to train or compare? Right. So we wrote a very good question, and we wrote actually a paper on how to measure the quality of data sets. So we have some ideas, right, on what should be a high quality data set. You can take a look at the proceedings of the ACM CCS 2019 conference, where we published this work. And very briefly, I will mention a few of the things that you can do. One of the things that you can do is what we call a small data set experiment. So take a very small sample from the data set and then just train and test on the rest of the data set. So for example, we did this experiment with our own data set, which we designed for phishing, right? We took a sample of about 50 phishing emails from about, I think, 5,000 or 6,000 phishing emails, and about 50 legitimate emails. So very small sample. And then we trained on this very small sample several classifiers. Okay. And then we ran these classifiers on 98% of the data set that we didn't train on. Okay. And we found some very stunning results. Some of the classifiers were doing at 90%, with just this small data set experiment. And so it was pretty clear that there was some features being leaked by the data set. And then we did a thorough cleaning of the data set and then did this experiment again. So there are many things you can do. You can measure the diversity of the data set. So you can take a look at that paper for other ideas. I want to move to the next question. Which type of features are most important for phishing email detection system? So that's also an excellent question. So the features that you would like to focus on should be, let's say, invariant features, right? Invariants of phishing emails that are those phishing attacks must have, right? And then, they must be in some sense also distinctive, not just invariant, but also distinctive, because you should be able to distinguish the legitimate emails from the phishing emails, right? So there are two qualities that you look for: distinctiveness, right, or distinguishing ability, and also invariance, right? And so, for example, one of the key features of phishing emails that we focused on was, okay, this has to have some kind of deadline, urgency, or financial incentive, and so on. Okay. So I'm going to go to the next question now. Can I use the word embedding techniques, or how much helpful if I use word embedding techniques? Great question. So we did use word embedding also in our work on the IEEE Access journal that I mentioned. So we are using word embeddings and then combining them with deep learning. So you can take a look at how that performed, and how that compared with other classifiers as well. So in the paper, so word embeddings are useful. That's the short answer, right? And the better the word embedding, the better your automatic detection system, right? So it looks like that's all the questions that are there in the chat. And so I would like to once again, thank all of you for listening, for giving part of your evening on Saturday, on the weekend, and coming to the presentation. And also, thanks a lot, Deepak, for everything.
Thank you very much, sir. And good morning to you also, because it is around 8 o'clock.
Yes, that's right. Actually, I got up for this talk at like 5:45. So it's pretty interesting, yeah, all the challenges we are having with this virtual format.
Okay. So thank you very much for your valuable speech, and it will be helpful to our participants also. And you see, in near future, if you organize such type of event, we will again request to you for your valuable speech.
Oh, thank you. Thank you.
So now we are going to the end of the session. So today, Professor Willie Susilo from Australia, he has given the talk on public key encryption with multi-hypertext equality test in cloud computing. And then Dr. Yang Lee today has talked about the physical attacks and their countermeasures. And then Dr. Susmita Ruji has given talk on the application of the blockchains. Now they are very interesting talk given by the Professor Rakesh Verma. He has given the talk on the data science for cybersecurity. So thank you very much to the all participants for your patience. And my thankful gratitude will go to the all eminent speakers, today's speakers, Professor Susilo, Professor Verma, and Dr. Susmita and Yang Lee. So from your busy schedule, you have given the talk. We are our attitude goes to you. And last but not the least, I thankful to our webinar team, PM Kumar, from the very beginning, from the session one. He has continuously helped to us to organize such type of event. And my thankful to our honorable Vice Chancellor, sir, for his continuous support and encouragement to us to organize such type of events. So thank you all, and that is for okay, sir. Thank you very much. See you again in near future. And I also send that HCM links to